I'm gonna have my telescopes up and running as well for regular imaging tonight. So
Okay.
after probably about 10 o'clock, 10:30 Central Time, it'll be dark enough here. Or earlier than that, I can show the moon if we need a little bit of space filler.
I'm thinking doing the same thing, Molly. I'm gonna bring out and do a couple of smartphone things.
And I've got two people that I invited over from Fraser Cain's program, the Virtual Star Party series that we had to cancel the series because there's never enough people available with clear skies. But I've invited two of those guys on as well, and it sounds like they both are going to have clear weather. So we'll keep our fingers crossed.
Jeff Wise beat everybody to the chat. He's the first one to log in. It's always a contest. Hey, Jeff, you're listening to us. Is my volume okay? Norm Hughes says, good evening. Panel of distinguished guests and speakers.
I think your volume's just fine, Scott.
Yeah, sometimes it sounds good to the other people, but it doesn't sound. Oh, Jeff Weiss says perfect volume. Okay. All right.
Yeah, it's not bad. It's not echoey like it was earlier, actually.
It's not? It sounds echoey to me.
Oh, weird.
Yeah.
Sounds normal on this end now.
Good. Perfect.
Also, I have a mechanical keyboard, so apologies in advance.
Right. Well, Molly, we are all excited to have this program and having you as the special guest.
Yeah.
So that's awesome.
Yeah, I'm really excited to do this.
Yeah.
And to have all my friends come on.
Yeah.
Okay, everyone, smile. I'm going to take a selfie.
Okay.
All right, there we go.
Was it just you in the selfie, or?
Oh, it's a snapshot for everybody, with everybody.
Okay, good.
Yeah, it's like an e-selfie or whatever it's called nowadays. Let's see. Global stop.
I often ask people just to spend, I only ask for 5 minutes a day, and only 5 minutes, but just 5 minutes where you only think of me. Just 5 minutes. Yeah, is that too much to ask, really?
Well, it depends on the context. I mean, people may think of you because they like you, or they may think of you because
they hate me, right?
Yeah. So maybe you, alongside the request, you want to kind of put some.
If 5 minutes is too much time, then just 60 seconds and $5 sent to this address. Okay. Right? So.
Can I hire you as a fundraiser?
Scott, how about $60 and how about $60 in 5 seconds, Scott? That's even better.
That's a deal.
Or you spam Facebook with 1,000 posts a day, and people can pay you to stop.
Stop. I'm already there. So.
like the modern day version of putting pink flamingos on your friend's yard and having them pay you to move them to somebody else's yard.
That's right. Yeah, a million pink flamingos. Yeah.
Yeah.
Yep. And you have a pink flamingo removal fee.
We almost did that on the cross country team as a fundraiser when I was in high school.
I like the way you think.
We did a ding dong ditch to bring gifts to our graduating seniors one year.
How did it work out?
It worked out pretty well, except I had a broken ankle. Well, it was at the healing stage where I was off crutches, but I was still wearing a boot, and I couldn't move very fast.
That's hard to run away.
It was a little difficult.
Coming out with the shotgun, yes, with a boot on your foot. Yeah,
it was okay because we had a sleepover one time, a big team summer party, and part of the team didn't come, but then went and TP'd us instead. It was very weird.
Brutal.
I think it was planned.
So we have so far. We've got, of course, I mentioned Jeff Wise, who's on, Norm Hughes, Chris Larson says hello, Molly, Jeff, Norm, and Scott. Ronald Green says hello. Somebody named Molly Wakeling is on.
Oh, I thought I was logged into my Astronomy Molly account.
Molly, that's right.
Oh yeah, I am logged into my Astronomy Molly account.
We've got Richard Grace on the other side. He's normally on this program. He says, not going to make it to the show tonight, just tired. Glad you got a packed house anyways. Oh, and howdy, everyone.
Well, it will be on YouTube after the broadcast ends.
Yeah. Cameron Gillis, he's on this side of the fence this time. And Rick Darkmoon, what a cool name.
Oh, yeah, he's a friend of mine from when I lived in the Midwest.
Yeah, Louisville, Kentucky, tuning in.
Yeah. He's the one. He gave me the Newtonian that I'm currently using for my my science rig that I do AVS observations with.
Oh, very cool. Very cool. All right. So this is an outreach program, and if you would be so kind as to share this broadcast before we get going to your favorite groups, or if you're on YouTube, just subscribe, and Facebook, of course, if you like, that would be nice. And I'm going to share this with a number of groups here. One of the groups I like is the Dogs and Cats of Astronomy.
There's a group like that.
Dogs and Cats of Space and Astronomy. Excuse me. Yes.
Is it which social media platform are we talking about?
That's Facebook.
Okay.
I've been meaning to take some of my astro photos and like Photoshop my cats into them in various poses. I started the project. I haven't actually made any images yet, but started going through and picking out the ones which are good candidates for creating such images.
How do you get a cat to pose? That's what I want.
Well, you just got to catch them, you know, got to be quick with the camera button. And also good at the Photoshop.
Yes. Okay, we're going to share with our friends at Facebook Astronomy Club, one of the biggest clubs out there. We shared with the Neil deGrasse Tyson group. That's 100,000.
Oh my.
See how many of them watch us tonight. We got Telescope Addicts.
Oh yeah, I think I'm in that group.
I'm in that group, huh?
Oh no, I'm not in that group. The Astro Imaging channel is in that group, and I cross-post from the Astro Imaging channel group over to their group for our Astro Imaging channel broadcasts.
Imaging.
That's right.
Must be 2 words. Backyard Astro Imaging Club? No? Maybe I don't belong to the group yet. Have to change that. RIT Astronomy Club? How about them? There is the Online Astronomy Society.
We're all very quiet right now, lost in deep thought and prayer.
I'm throwing Facebook posts around on Facebook. Ooh, Twitter.
I couldn't get my internet to work, so I threw the computer across the office and out the window and then brought it back in, and now it works just fine.
That's fine.
That does seem
And
to
I hear
work
you
very
guys,
well.
Scotty.
That's artificial intelligence, David. The computer knows you're mad at it.
Yeah.
Or you just forced it to turn off and then back on again.
When I was in undergrad, I worked in IT in the dorms, so did like front end IT support for the students. And it was a very frequent occurrence that I'd get a call and I would head over to somebody's dorm room. And as soon as I walked in, their problem was fixed. Like the thing that was being weird stopped being weird. And they'd be like, I swear that it was broken. I said, it's just intimidated by my presence.
There's this AI robot now that's in development for use on the ISS that if you don't engage it, one of the astronauts, for a certain amount of time, it will turn on and say, I'm disturbed to sense that you may not like me. This is getting to be a little bit weird, isn't it, with AI now?
That sounds like a HAL 9000 to me right there. So. Bought one of my friends a HAL 9000 model. It's a panel with the red dome on it. His first question is it going to try to kill me?
Just don't try to unplug it. Whatever you do. Yep.
Whatever you do.
And don't leave the pod bay doors locked.
Always leave that one unlocked. Mm-hmm. Well, we are sharing this also with a lot of our astronomy clubs that serve Latin America, Astronomia groups, which is great. Lots of interest.
Now, Scotty, I kind of find it very hard to hear you right now.
How about now?
That's much better. Much
Much
better.
better. I just got to get my voice next to the microphone.
As do I.
Yeah. Yes. Okay.
Let's see. What do we have? Oh, good. Michaela's here. Michaela!
Hello.
The curler! Michaela is my minion. My protege, if you will.
Better than minion.
Hi, Michaela. How are you?
Good. How are you?
I'm doing well. I'm Stella. We rhyme. Michaela and Stella.
Yeah.
Sounds really cool.
It does rhyme, yeah.
Yeah.
I should start my camera cooling down. On one of my cameras, it gets a frost spot on it if I don't cool it down really slowly in like 5-degree blocks over 5 minutes. Like it's really picky.
Yeah.
How many rigs are you going to have out tonight, Molly?
3.
3. You got the drive for working on the other one, eh?
Well, my Celestron AVX mount still, like the deck motor still like kind of jumps every once in a while and I can't guide it, but if I limit it to 60-second exposures, most of them turn out okay.
Cool. Awesome.
Yes, I use that one as the science rig since I have a CCD on there and can bin 2x2 to get better sensitivity.
All right.
Looks like we're rolling.
We want to find Earth-like planets around sun-like stars, because that's our best chance of finding a world with life on it.
Today's the day that truck carrying the NUID instrument has arrived. Over the next couple of days, we'll start integrating the whole system together. But the first step is to actually get here, and today the instrument got here.
The instrument is a radial velocity spectrometer. It measures to very high accuracy the wobble of a star as a planet goes around it. We are trying to do this to a level of sensitivity more than anything that exists at the moment.
We're really gunning for is one of the most precise measurements of a frequency in astronomy. And I'm hoping we can get down to the point where we're really probing the limits of the star and nothing else. The idea with NUID is really develop something that is so stable that you're purely dominated by stellar astrophysics.
Not only will it detect planets and measure masses of known planets, but you can try for direct detection of planetary photons, so that you can try to disentangle the very small reflected light signature from the planet itself. Instruments like NUID present the first capability for being able to do it.
One of the things NASA wanted was an instrument that could actually help the community follow up test objects.
I think it'll be a very valuable resource for confirming test planets. So TESS provides the one half, and NUID I think will do a wonderful job providing the masses for a lot of these confirmed planets.
Another goal for NUID is to identify potential targets for JWST, because JWST will open the doors to characterizing these planets by actually looking for atmospheres and images. And so it's very important that you find the right ones to spend time with the telescope.
Well, hello everybody. I want to welcome everyone to the 39th Global Star Party. And our special guest tonight, guest host, is Molly Wakeling. Now, Molly has been with us on many of these Global Star Parties. She's done some special programs with us as well. What I know about her is, of course, she's fabulous to get along with, but she's a great astrophotographer. She likes to do a lot of outreach through the virtual programs that we've been doing, but she also likes to get out there. She has her own trailer set up so that she can get out to remote areas when she can, but she does a lot of imaging right from her own backyard. She got started in astrophotography in the summer of 2015, and she has really just pushed herself to do some remarkable imaging. She knows a ton about image processing, and she's always willing to lend a hand. And she's very connected. She knows a lot of people here, which is awesome. And apparently she only just scratched the surface of all the people that she could have invited onto this program for this go-around. So we're going to have another Global Star Party with Molly hosting it so that we can get more of her friends on. You're also involved in STEM outreach, and you have, it says here, and maybe you've already improved on this, over 100 hours of volunteer activities reaching over 1,000 people. You're an AA VSO ambassador and broadcaster on the Astro Imaging channel on YouTube. So, Molly, thank you for doing this. You're making my job easier tonight, and I'm going to turn this over to you, and you can kick off this program. Thank you.
All right, Scott, thank you. And thanks so much for inviting me to co-host the show and to bring on a slew of, I think, are going to be fantastic speakers and presenters and some live telescope views as well. I wanted to, for this session, go with a theme of highlighting women and young people in astronomy. When you look around your astronomy club or at your star party, women and young people are the two people you are least likely to find there, I say from experience. The first summer I went down to the Texas Star Party, I had my car piled up with gear and I pulled through the gate and there was a gal there checking people in and looked at me and looked how, in the absence of a spouse, and looked at the back of my car and said, "Are you a woman astronomer?" And I was like, "Yeah." And she was so excited to meet another one. There's very few of us.
Right.
So I wanted to highlight some of the other women and young people that I know in astronomy to kind of show everybody else that that we're here and you can be too. There's so much opportunity to get involved in astronomy, either in the astrophotography front or doing STEM outreach or all kinds of things. And wanted to highlight those people and invite everybody to come participate in astronomy.
Great.
So our first speaker tonight is the famed David Levy. He is, if you're unfamiliar, if you don't watch the show, he is the David Levy of the Comet Levy Schumacher fame, in the one that crashed into Jupiter, has discovered and co-discovered numerous other comets, has authored 34 books that, according to Wikipedia, was including a biography on Gene Shoemaker and Clyde Tombaugh, the discoverer of Pluto, and is a prolific astronomer. And he always has really cool poetry on this show and really amazing stories to share from his time in astronomy. So thank you for coming back on this week, David.
Well, thank you so much, Molly. And it's really a pleasure to be here to add my welcome to all of you tonight around the world. And we have a lot of people, very interesting people tonight, a slightly different group from what we usually have. I'm really looking forward to Stella's presentation. And I think that we're going to have something very interesting and very unusual tonight. I'm looking forward to all of your presentations. But I'm asked to open up these star parties because I offer a little bit of poetry to get us into our session. And tonight we're going to go back to Shakespeare. And the first, I have two quotes from Shakespeare to offer tonight. The first is one that I believe I gave last week, but I'm going to give it again because it is so powerful. And then the second one is one that I did not give last week. You imagine Shakespeare sitting down at his computer and opening up Microsoft Word version minus 6008. And he's at the part of his play where he's about to announce that Macbeth's wife, Lady Macbeth, has just passed away. And he's thinking of what to write. And the queen, my lord, is dead, is what he has just written. And Macbeth starts to write, she should have died hereafter. There would have been a time for such a word. And then you kind of imagine there's a tap on his shoulder. And Shakespeare turns to his left, and it's God who is looking at him, and he or she says, Will, go take a break. I'm going to take over for a few lines. And this, you got to say, is something that does have divine inspiration, because he talks about space and time and the continuum. And this is the quote that he comes out with, to which I'm going to add one final line. Tomorrow and tomorrow and tomorrow creeps in its petty pace from day to day to the last syllable of recorded time, and then is heard no more. Out, out, brief candle. Life's but a walking shadow, a poor player that struts and frets his hour upon the stage, and then is heard no more. It is a tale told by an idiot, full of sound and fury, signifying nothing, signifying everything. The second quote is from Hamlet. And I think a lot of you will be familiar with this, especially those of you who are Star Trek fans, because again, there's that episode in which Patrick Stewart, playing Jean-Luc Picard, he says, what Shakespeare writes with irony, I say with conviction. This most excellent canopy the air, look you, this brave or hanging firmament, this majestical roof fretted with golden fire. What a piece of work is a human being. How noble in reason, how infinite in faculties, in form and moving, how express and admirable, in action, how like an angel, in apprehension, how like a god, the beauty of the world, the paragon of animals. And yet to me, what is this quintessence of dust? And on that note, I'm going to hand it back to you, Molly. Thank you for giving me this opportunity.
Thank you so much. I was, when you see a lot of these astronomy outreach shows, it's a lot of technical work and a lot of, regular astronomy things. But on this show, we get to have some really cool poetry by some amazing people and presented by David Levy here. So it's always a delight. So next on our schedule is David Eicher for a special presentation, in quotes.
Well,
I don't have an introduction for you, unfortunately.
That's okay. That's okay. Thank you, Molly. Today I wanted to do something that was a little unusual, and that is to talk a little bit about my dad, who was a scientist, and today is his 100th birthday. Now, we lost him at age 95, but he was an influence with Astronomy magazine and with Deep Sky magazine, if you remember back in the day, that publication. And his sort of outlook on life and inspiring view of things is important, I think, to us to remember. So I'd like to talk a little bit about him tonight. He was a professor of chemistry, a Manhattan Project scientist, a philosopher of science. He taught the philosophy of science, and a humanitarian. And I think it's important to remember someone who goes through their entire life continuing to evolve and to learn as much as possible, always, that curiosity is a huge driving factor for us who care about understanding the way things really work. So he was very interested in many, many things. He was passionate about all of his interests. He was a lifelong learner, and that, I think, falls in line with what a lot of us in this group and talking to each other about our interests are like. He was an absorber and a sharer of everything that he cared about for many, many years. Many things fascinated him. He taught school because he continued after his emeritus retirement from Miami University in Ohio to teach an institute for learning in retirement at Miami. And so he taught a grand total of 50 years as a teacher, 37 years in university, and even thereafter, he taught. He never sort of lost that fire for learning about things continuously and sharing what he learned and what was evolving in knowledge as he went along. And that's really critical, I think, for us to keep close to our heart as well. He wrote about a lot of things. He inspired me to write and to learn about lots of things. He wrote a lot about World War II that he was involved with as a civilian. He wrote a lot about the Civil War that he had ancestors in fighting for Grant and Sherman. He wrote a lot about atomic energy that he was involved with when he was but 21 years old. Went directly from his undergrad school into the Manhattan Project. He wrote about the West and mining and mineralogy a lot, and back in starting his adventures going out west from growing up in Ohio with his parents who could travel extensively in the old days. And so they explored the West through long trips that inspired him beginning in 1926 when he was very young. He wrote a lot about the philosophy of science. He wrote about codes and ciphers that fascinated him. He wrote about stamps and coins and was interested in collecting artifacts and in museums being the sharing of artifacts that collect our knowledge, of course, together from the root word. And he wrote a lot about American history. So I'd like to share, if I can share my screen, I'd like to share just a few images of him and talk just a little bit more about how he inspired me. Now, I am sharing Microsoft PowerPoint, not my desktop now. Let me see if this works. Can you see what I am seeing?
Yes.
And can I start a slideshow? And I'll show a few pictures of him.
Perfect.
Now, here is John at soon after his birth with his parents in Dayton. He grew up in Dayton, which on Ruskin Road, a nice little house that was built in, they moved to from a couple of simpler houses to a very nice house that was built in 1929, where they were up until World War II, when he went off to work on the project. And he lived a couple of houses down from a famous woman. And he got to know quite a number of people around Dayton. Of course, Dayton was the birthplace of aviation. He was fortunate enough to live 2 houses away from a woman called Ivanette Wright Miller. And she was the niece of the Wright brothers. Now, when he grew up there, we think of how incredibly distant to many people now the early days of NASA, of space flight, seem to us now, which we love. The exploration of the moon, the Apollo days. Unfortunately, we're losing many of those astronauts now who are still our good friends, some of them. But here's one lifetime, goes back all the way to the invention of powered flight, even, which is incredible there in Dayton. Of course, Wilbur, by the time my father was growing up there, was long gone, but occasionally, every once in a while, a big black Ford touring car would pull up to Ivanette's house as my dad was out playing with his friends, and Orville Wright would get out of the car and he would talk to Orville Wright, so that's incredibly close to us still. In the sort of tapestry of history, if you will. And he was a stamp collector at that time. Mrs. Miller thought he was a cute kid and took a shine to him. And so one day she invited him up to her attic to pick out a nice stamp for his collection to have. And he picked out a nice envelope. And he regretted this often for years later, but he pulled the letter out and handed it back to Mrs. Miller and only kept the envelope and stamp, thinking he shouldn't keep the letter. Well, and here's the envelope. It's an envelope that is from Jimmy Doolittle in 1932, addressed to Orville Wright.
Wow.
So you can imagine what the letter was about here.
Oh my goodness.
This was, of course, Jimmy Doolittle became very, very famous, of course, among other things, for Doolittle's raid during World War II and so on. So here he is as a young child in about 1925 here. Just to talk a little bit about him. He had this thirst for knowledge and excitement about science, which of course was really taking a hold in the early 20th century, of logic, of an analytical thinking, of experimentation. All those hallmarks of science were very important to progressives, of course, at that time. This is John about the time that he went to work for the Manhattan Project. He worked for Harold Urey at Columbia University in New York, the original portion of the Manhattan Project, and what he worked on was the expansion rate of the gaseous expansion rate of uranium hexafluoride, which was an important component to understand, so that the scale of Oak Ridge that created the uranium material for the Manhattan Project could be worked out. So that's what he did there at Columbia. That interrupted, of course, a lot of people's lives. He went back, he got his PhD at Purdue, and he became a professor at Miami University of organic chemistry. He was there for 37 years teaching at Miami, the original Miami, that is, in Ohio. He got into lots and lots of writings and was very interested in, he was able to track what was happening in World War II from afar. He always joked that he helped to successfully defend New York City from the Nazis. But he was also interested, as I said, in the Civil War. And so later in life, after my mother died, we took a lot of trips together and got into relics and artifacts and papers that we had together of writing about the American Civil War as well. And this is how he looked in 1982, about the time we were cranking up and working on Deep Sky Monthly, the publication that I started as a 15-year-old and led to my involvement in Astronomy Magazine, and so on. The first issues of which rolled off of his mimeograph machine at Miami in his office. It was very sophisticated stuff. And he always supported, to a great degree, my interest and the interests of others. Not only was he curious and a lifelong learner and fanatically interested in understanding the details of things that's really critical for us as people who love the universe and love astronomy, but he was genuinely interested in people. And that's a really important aspect of us too, of the scientific reasoning. And I think that's why we're here on a program like this tonight, and what you do, Scott, for us and with us here. And he would be delighted, I think, to know that we are doing this kind of discussion continuously of things, which is exactly what he thought should be done more and more among science-minded people. This is a shot. I'm sorry, Scott.
I said thank you.
Yeah, absolutely. And this is a photograph of him in 2014, near the end, a couple of years before the end of his life, in his old chemistry office at Miami there that I took. And I wanted to just end with a couple of thoughts from him. He was not a particularly conventionally religious guy. He was a scientist, an empiricist, but he did co-found 2 Unitarian Universalist churches, one in West Lafayette, where Purdue was, where he went to school, and one in Oxford, where Miami was as well. And a few years before his death, he came up with a revision of what he called a religious credo, 10 Commandments for Scientists. So I thought I should share this with you as well. And I won't read through the whole thing. You guys know what these are. But a religious credo is a guideline for life, a suggestion of purpose or a goal. 10 is an arbitrary number for convenience, as we know. And you guys know what commandments are and natural theories are. So he included the conservation theory, entropy theory, quantum theory, radiation theory, particle theory, these scientific theories, not theories meaning hypotheses, ideas, but these are tested, known quantities that science follows, these theories in the scientific sense. Evolution theory, relativity theory, and psychological theory. And John, although he was a pure scientist and loved people, he had a bit of a soft spot underneath him. And so he had 2 final ones here that I thought I would read. Behavior theory. There's satisfaction in helping others toward happiness, which is often reciprocal. Personal immortality is achieved by the views of others. And lastly, ethical theory. For a worthwhile existence, we must strive together to maximize freedom with responsibility and find fulfillment in peace and in love. So that is a quick group of thoughts from John Eicher, who was very inspiring to me and my closest pal and working on lots of things, and very inspiring to what happened with the evolution of Deep Sky and of Astronomy magazines. So he would be proud to know that we're all talking about all this scientific stuff together now. So thank you for listening to me, and happy 100th birthday to my dad.
Happy birthday.
And I will...
David, if you don't mind, I'd like to say a couple of things about this.
Of course, David, because you know John David quite well.
Yeah, I knew him. We watched the movie Lincoln together.
Yeah.
Wendy and I and you and your dad watched that movie together here in this house.
Yeah.
But I have 2 words to say about your presentation tonight. Home run.
Oh,
I've heard many presentations you've given. This one is by far the best one I've heard. And it reminds me so much of my own dad, who I was also very close to.
Yeah.
And, if you're wondering how long you're going to miss him, my father died in 1985, and I'm getting around to not missing him as much as I used to, but give another 15, 20 years and I may get over him, but not quite yet. I remember stories about my father, who was a big help in my early years in enjoying the night sky. But I had a special friend, a Greek amateur astronomer named Konstantin Papakosmas. And he was all the friends that I've had. He was the one that Dad loved the most. And as my father was slowly dying by inches from Alzheimer's disease, one day Konstantin came into the house and Dad could barely remember who he was, who he himself was, but he never forgot Konstantin. And I remember one day Konstantin was there and Dad looked at Konstantin and said, "Do you know what's going on with me?" And Konstantin said, "Yes, I'm afraid I do." And Dad looked at Konstantin and said, "I can't live like this. I wish I were dead." I'll never, ever forget the look on Konstantin's face when Dad told him that. And I know that you must miss your dad in a very special and personal way. And I want to thank you so much for sharing this incredible thought with us tonight. David, it was really, I thought, the best of all the talks I've ever heard you give. I just wanted to tell you that.
Thank you so much, David. And thank you for your thoughts about your dad as well. Thank you.
Right.
Thank you so much for telling us about him and telling his story, and what a remarkable man. And thank you for your thoughts as well, other David.
Thanks, Molly.
Well, our next guest is my minion, Michaela Weller. We met when I lived out in the Midwest before moving out here to California in the same astronomy club. And as we were kind of learning astrophotography together and working on that skill, she will be graduating with her Bachelor of Science in Astronomy and Astrophysics this coming May from the Ohio State University. You're welcome. Sorry, Michigan people. She's planning on attending graduate school starting this coming fall to pursue her PhD also in astronomy and astrophysics. She is currently researching as an undergraduate, which is awesome, the formation of compact binaries. And for her graduate work, she's interested in researching in areas of nucleosynthesis, spectroscopy, or nuclear astrophysics, all things that I also love. She is going to give a talk tonight on her current research of compact binaries and how we use radio velocity to detect them. So Michaela, take it away.
Yeah, thank you. I hope my internet holds out. Sometimes when I'm doing Zoom, it doesn't.
Yeah.
So
far so good.
Yeah.
Very good.
So everyone, as Molly said, my name is Michaela Weller. I am a fourth year astrophysics major at Ohio State University. I did not include the, but
I'm shocked.
So I won't go through the spiel, but I am getting my BS in May. I don't know where I'm going to go to graduate school quite yet. I'm hopefully waiting on a few more offers from my top choices, but I really am excited. So throughout this talk, do feel free to ask any questions. I'll try my best to answer them. And I'm going to try to leave a few seconds or something at the end for questions as well. So today I will be talking about my second undergraduate research project. I started this in the summer of last year through the Summer Undergraduate Research Project at Ohio State. As you can see from the title, my research is about using radio velocity variations to hopefully detect compact remnants, which is mainly black holes and neutron stars orbiting massive living stars. So normally finding these systems is done through other means of observation, like through detection of X-ray emission due to accretion from the secondary. But these in general only account for a small fraction of the total number of these types of systems. So finding other ways to try to find these is very important. So before I dive into what all of that meant, I want to talk about why these systems are even interesting to us. So back in 2015, as I'm sure most of you remember, LIGO directly observed gravitational waves for the first time. It was very exciting. And this was a result of a binary black hole system merging together to form one supermassive black hole. And through this process, gravitational waves were emitted and detected after first being theorized by Albert Einstein many years ago. And if you're looking at the numbers on the screen and adding up the masses, you will actually see that there is a difference of about 3 solar masses between the final mass of a supermassive black hole and the masses of the 2 separate black holes. And I think Molly knows where I'm going with this, that we all know Einstein's famous equation, E = mc², which relates mass and energy. So we see where the 3 solar masses went, which is the energy put into the gravitational waves, which is so cool. And this is why we are interested in finding these systems, as we want LIGO to be able to have potential sources to look for in the future, hopefully before they merge. So there are a variety of different ways these compact binaries are created. And I mainly focus on neutron star binaries, binary black holes, or a system with 1 black hole and 1 neutron star, because in the event of a merger, all of these will emit gravitational waves. The type of formation I use in my paper is when they were binaries from the very beginning, so an initial binary population. However, this means that the system has to survive the first supernova kick from the massive primary and does not get disrupted. And here, disruption just means that the secondary star is kicked from the system and is no longer gravitationally bound to its companion black hole and neutron star. Also, these systems can merge when in other stages of evolution, depending on orbital parameters, common envelope phase, or mass loss. So we may not always end up with 2 compact remnants. Another quick example of formation is a capture event in which 1 black hole or neutron star captures another compact object in its orbit, but that wasn't included in the package that I used for my simulations. So now I want to talk about what radial velocity even is. I'm sure many of you guys have heard it before, but maybe not have a good conceptual idea of it. So by definition, it is basically the component of the velocity of the object that is along the line of sight of an observer. So when the object is moving perpendicularly to the observer, the radial velocity is 0. And when the object is moving parallel to the observer's line of sight, then the radial velocity is not only non-zero, but it is also at its maximum magnitude. This setup sounds very much like a sinusoidal curve, just a sine wave, which is what we actually do see, as I will show a bit later. Although this curve in practice will have different shapes due to eccentricity and things like that, but a sinusoidal is a good approximation in general. This image is a good illustration, though a planet is used instead of another star, which is what I focus on. This is likely because the radial velocity method is used for the detection of exoplanets, which is a very hot topic in astronomy that I am not part of. Nonetheless, it also shows the barycenter, which is the center of mass for the system. Oftentimes, the barycenter for a planet will actually be somewhere in the star, but for massive planets like Jupiter, the barycenter is right outside the surface of the star usually. So let's talk observational techniques. How do we measure the radial velocity? Can amateurs measure radial velocity? The short answer is no and yes. You have to have a spectrograph handy and a really nice telescope for maximum resolution, although the error does tend to be a bit larger with amateur equipment. It's not impossible though, especially if you have the time, money, and the drive to do it. But to measure the radial velocity of a target, we actually measure its spectrum. And we actually know which element corresponds to which wavelength from measurements in a lab. However, when we gather these spectra, these lines are typically redshifted or blue shifted by some amount, which is just a shortening or lengthening of light, as these targets are pretty far away from us. And since we know what these lab values are, Here, the lab value is the picture at rest, and we can compare our measured values from the spectrum that we take and see how shifted the lines are. And we can plug these values into the Doppler shift formula, and we get a radial velocity out of it. Large surveys like the Sloan Digital Sky Survey do this, but things like resolution matter a lot too. And they also only observe a target an average of 3 times, although some stars have a lot of observations, but what I found, it was about 3. So they don't get the entire radial velocity curve, which I did incorporate that into my simulations as well. So getting into my research some more, the main question I sought to answer was how many of these compact remnant binaries can we expect to see, mainly in our galaxy alone, that surveys like the Milky Way mapper can observe in the future. To answer this question, I simulated a population of binaries using COSMIC, which is the Compact Object Synthesis and Monte Carlo Investigation Code. And it is simply a Python package where I can set certain parameters and prescriptions to create an initial binary population. Then, through the evolve class in COSMIC, I can evolve these systems for however long I want, but I set the systems to evolve for the entire lifetime of the universe to make sure we got mergers. Although, in theory, massive stars evolve quite fast compared to lower mass stars. So maybe 1 billion year would have done the trick, but I just stuck with the default parameters. So the output of COSMIC gives a lot of data, including kick info information, that contain various useful parameters that describe the binary system at every time step, which is just important epochs within the evolutionary history of the system, such as the moment when one of the stars moved to the Hertzsprung gap on the HR diagram, or when Roche lobe overflow commenced. And there's a lot more examples. But anyway, these parameters include things such as the masses of the stars, the orbital period, the semi-major axis, and a lot of other things. And with these parameters, I am able to calculate the semi-amplitude K, which is about 30 kilometers per second here, and radial velocity as a function of time, in which the entire curve is seen in blue in this plot. Again, large surveys don't get this blue line. Instead, we get these flag points. I do randomize some angles that describe the orbit, such as the inclination angle and the argument of periapsis, because these aren't included in COSMIC, but I do incorporate the delta from the supernova. So that's really cool. But having the radial velocity as a function of time is useful because we now have the ability to know the radial velocity at any random epoch. I am even able to mock real observations, like from those surveys I mentioned prior, where we have some data points within a few days of each other, and then a few more observations after months or years later, which can be seen in this plot as the black points. This is known as the cadence of observations. Nonetheless, you can see the blue shift, which has negative velocities, which is motion towards the observer, and red shift, positive velocities, which is motion away from the observer. So the maximum radial velocity of the system is about plus or minus 30 kilometers per second. And again, when the RV is 0, the body is moving directly perpendicularly to the observer. But another more useful parameter we can measure is actually the spread in the RV from the observations. So here, the magnitude of the spread in RV is about 40 kilometers per second, since our most positive velocity observed is about 10 kilometers per second, and our most negative velocity observed is about negative 30. So, oh, I don't know where that one came from. The most important thing to take away from this plot is that the maximum delta RV is large. The error bars indicate that if we got more observations, such as 10, then our maximum delta RV will approach the true value of the system. So that's only a bit about my research. I will say that our results are quite encouraging, and I am excited to see if any systems can be detected. I am currently writing my paper on this topic, so I don't want to give away too much before it's published. So that's all I have. Are there any questions?
Haven't seen any come up on YouTube yet, which is also getting the chat from Facebook and Twitch and whatnot. But does anybody in the room have questions?
Yeah.
David, you're muted.
I'm muted. I'm also going to COVID shot tomorrow, Moderna, and I have heard that everybody who has gotten a second COVID shot has died from it. So next week you're going to hear me beyond. But in any event, I just wanted to say that to hear a presentation about so specific, I'm trying to juxtapose it with David's talk that is really, I found overwhelming. And I just say that I really enjoyed your presentation so much. And just to be able to compare the detail contained in it to the generalizations that David had offered and that Molly has been putting in is just wonderful. Thank you so much for sharing what you're doing, your research with us tonight. Thank you.
Yeah, thank you. I appreciate that.
Still nothing in from YouTube, although people say they liked your presentation, and seems like you're doing just fine from one of our commenters.
I will add that during Michaela's presentation that we had another 11 shares on Facebook. So we're up to almost 60 shares right now. So people liked it, Michaela.
Yeah, that's good to hear.
And I'm duly impressed with what you're working on and what you know. So that's very cool.
Thank you. Yeah. I mean, my graduate research will probably be a little bit different than this, but it's been really fun to work on this. So
great. Yeah, I really hope that you come back on the program. It's
yeah.
And that goes for everybody on here, but you know, it's so inspiring to see you know, a young person get so involved in science and astronomy in particular. And so, you know, I can only imagine you have an extremely bright future ahead of you.
I sure hope so.
She does indeed. She doubts herself, but she doesn't need to. See, I told you.
Yeah, very good.
All right. Well, thank you so much, Michaela, for your talk. It's fun to get some real hard science on here, as well as all of the kind of more day-to-day astronomy stuff that we tend to see. So that's really cool. Thanks for coming on, and feel free to hang out in the room for the rest of however long you want to be online for.
I really appreciate it.
All right. So our next guest is Dr. Stella Kafka. She is the Executive Director and CEO of the American Association of Variable Star Observers, or the AAVSO, which is an international organization focusing on engaging professional and amateur astronomers in science. Within the auspices of the AAVSO, Dr. Kafka is working towards enabling individuals from all backgrounds to actively participate in research projects, building a community of science-savvy citizens who work collectively to understand some of the most dynamic phenomena in the universe. Which is, you know, really, see, when you think about the universe, like when we're looking through our telescopes, it seems like it's unchanging, but there's so much that's going on that that we can observe these changes with, and amateurs can get into that. Dr. Kafka acquired her Bachelor of Science in Physics from the University of Athens in Greece, and her Master's and PhD in Astronomy from Indiana University here in the States. Dr. Kafka's research interests are in semi-detached binary star systems, such as cataclysmic variables, which can become type 1a supernova. So Dr. Kafka, take it away.
Hi, everyone. This is Stella Kafka. And for this group, I am Stella. Molly, thank you so much for the wonderful introduction. You know, so many thoughts before I start with the presentation. And the first one that comes to mind is Newton's quote: "If I have seen further, it is by standing on the shoulders of giants." For most of us, those special individuals are our parents, who are always our cheerleaders, no matter what we do, where we are in life. and the tribute that was given to a father who was not only a cheerleader to an extraordinary individual, but also a very accomplished astronomer and very accomplished citizen of the world, is actually highlighting what our parents mean to us. I'm very fortunate to still have my parents around. They think I am the most extraordinary individual in life, and there is nothing that will ever change their opinion. But today, speaking of extraordinary individuals, when Molly invited me to participate in the Star Party and mentioned that she wanted to highlight women in astronomy, I thought of giants who have influenced science in unique and very powerful ways and did not gain much recognition until quite recently. And I love Michaela's presentation, not only because of for its scientific significance and inspiration, but also because it reminds me that we have gone a long way since even last century, and our future is bright, and our future is actually female. So today I would like to take just a little bit of time to talk about some of those women, the women of history, the giants in science, and their work, with a disclaimer that this is only a teeny tiny sample of the female intellect that has made extraordinary discoveries over time. And the interesting part is pretty much historically, we don't have much information about women in science, although we have indications that the contributions were substantial. The few that are mentioned in history is Elena Piscopia, who was the first woman to earn a PhD in 1678. So we're talking about recent history here. And Caroline Herschel, who's the first astronomer to be allowed to publish scientific results in a journal. And then, of course, it was a matter of time and a changing culture and also changing needs in science. In our modern history, before computers were discovered, women were used as calculators in science, simply because these were jobs that men did not want to do. Those tasks were extremely tedious. They required much attention to detail, and they're considered to be very trivial. So the women who were involved in this type of work were underpaid and overworked. This is a group that was employed by the Harvard Observatory director, Edward Pickering, at the beginning of last century, who was actually paying 2 women for the piece of 1 man, while all those women were cataloging data from photographic plates and were performing very complex mathematical calculations that required precise mathematical measurements and data analysis by hand. Remember, there were no computers at the time. There was no any other aid but their piece of paper and pencil and their eyes.
Wow.
So it was truly only on the 20th century when what we know now as computers and algorithms started being developed. So with that in mind, I'd like to introduce 4 women to you, without which computing and astronomy as we know it would not exist. And I want to start with actually the end of the 19th century, late 19th century, Ada Lovelace, one of the first known women mathematicians and computer programmers before computers existed. In 1837, Charles Babbage described his analytical engine, which could have been one of the very first early computers if it was fully built. Lovelace wrote an extensive, in-depth analysis of the engine, noting about both the technology and the implication of the machine. And actually, she would not be recognized until decades later. Her notes were published only in 1953. So she actually built a theoretical model of the first computer, a first computer algorithm, without even knowing what a computer looked like, or without even having something solid to work with and even test it. Fast forward, Heidi Lamar, Hollywood glamour, one of the most accomplished individuals in the entertainment business. She lived around 1942. And, you know, she's one of those icons that showcases beauty and grace. But what not many people know is that during World War II, in 1942, she developed a secret communication system that was a patent for an idea for a radio signaling device, which was a means of changing radio frequencies to keep enemies from decoding messages. Wow. The system became such an important step in the development of technology to maintain security of both military communications and cellular phones. And not only that, that technology would allow later the invention of wireless signals like Wi-Fi and Bluetooth. We wouldn't have Bluetooth right now, or it would look very, very different, or Wi-Fi if it wasn't for Heidi Lamar. Actually, World War II was a time of innovation in many different ways. No one supports war, but it kind of helps us push forward what we know or we don't know in order to protect our loved ones. So during World War II, Rear Admiral Gracie Hopper, who was actually working at the Navy, was sent to Cambridge, Massachusetts in 1944 and was assigned to write programs for Mark I, which was the first electromechanical computer, which actually ran ballistic problems for the Navy. Her work actually on Mark I began her career as a computer scientist, or whatever computer science could look like at that time. And later, she reimagined programming as a user-friendly language. And actually, she wrote the first compiler and developed programs for other machines. In her spare time, actually, in 1952, she created one of the world's first compilers. She envisioned a code to use English language-based instructions, and her programming language design work led to the creation of COBOL. How many people know what COBOL was?
Heard of it.
That was one of the earliest programming languages, and actually it is used to this day. So that brings us to the middle of last century, middle of the 20th century. The post-war era was extremely interesting when it comes to the attitude of society and of science and scientists when it comes to women. Around the 60s, software engineering was considered to be a woman's work because it was thought of as clerical. So hardware was a difficult work, and so it was a job for men. And actually Cosmopolitan famously ran a 1967 issue about the computer girls. However, women kept making a difference exactly because of not only their intellect and skills, and that was recognized at NASA to begin with when it comes to astronomy and the space program. So at NASA, things were very visibly changing. The first woman to break the gender barrier at the NASA Langley Laboratory, Langley Memorial Aeronautical Laboratory at the time, was Pearl Young. She actually arrived there at the beginning of 1920 as an engineer, and she became a chief technical editor for the National Advisory Committee for Aeronautics. But even more than that, an even bigger door opened around early 1930s when a group of women came to the center to form a computer pool. So the idea was that those women would be processing all the data coming in from wind tunnel tests and flight tests. It started as an experiment, but then very quickly it became much bigger than its intent. So in about just showcasing that, about 1942, human computers became so essential to operations at the center that a memo that circulated that April put it this way: the engineers admit themselves that the girl computers do the work more rapidly and accurately than they could. So women started being recognized for the work they were doing. And remember, there was a time where a computer would take space as big as a room. So we're talking about these huge constructions that had less memory and less computer power than what you have on your phone right now. And out of all these women, I would like to highlight this one. This one is, here we go, Katherine Johnson. She was a physicist and mathematician and actually came to NASA in 1953 as a human computer. And she eventually joined NASA's Space Task Force. By 1958, she has become an aerospace technologist. That was the title that was given to her. And eventually she joined the Space Task Force, where she calculated trajectories for some of the Mercury missions. And actually, Katherine Johnson calculated the first path for the first manned mission to the moon. And history tells us that But at that time, John Glenn was a little bit concerned about the calculations, the success of the mission. Remember, he was on that probe, right? And he famously said, get the girl to check the numbers. And he was referring to Johnson. Johnson was one of several women who worked the way out of the computer pool and actually went into engineering jobs, something that became more frequent through the 60s and 70s and moving forward. And actually, in 2016, it was a really nice movie that featured some of those brilliant women and the challenges as being, some of the computers and first engineers in a very male-dominated world. If you haven't seen that, it's called Hidden Figures, one of my favorite movies ever. So jumping to our century, as women, we are inspired by the work and lives of those extraordinary individuals. And as women in science, we're leading projects now, we're making recognizable contributions. We have our own place in society and our own place in science. We're making very strong marks. And actually, there are even apps where you can find out more about women in space science if you're interested in. So just check it out. It's open source to everyone. And also we have programs, or we're launching programs where we inspire the future generation and the generations of today and showcase them, mentor them to be the future and be themselves, be creative, be strong, be as amazing as they want, and actually channel all their energy to science, because we need everyone on board in order to understand the universe. And for that, I'm going to kind of throw something that the AVSO is doing. We have an ambassador program that is our way of engaging, inspiring, and cultivating younger members. And actually, Molly is one of the leaders of the program. She's one of the first individuals that joined that program. And this is a way to engage younger individuals in all kinds of activity, included but not limited to outreach, community engagement, variable stars, participating in public engagement, doing research, sidewalk astronomy, analyze data, anything and everything those young individuals want to use as their segue to introducing astronomy to everyone or empowering themselves. They're very welcome to do as part of our ambassador program. Our ambassadors, by the way, get a free AVSO membership, free registration for our meetings, you can publish in our journal, et cetera, et cetera. So this is the information if you are interested in joining the program, or you know someone who would be interested, please contact us and please spread the word. Some final thoughts. Women in science, or in general, a very diverse and inclusive scientific workforce, draws from the widest range of backgrounds, perspectives, and experiences. So it helps us maximize innovation and creativity in science. For the young people out there, you are the future. Join us, enjoy astronomy, have fun with the night sky. And if you think that the AVSO can help in any form or shape, please contact us. My email is here. With that, I would like to thank you for your attention and stop sharing my screen. There you go. All yours, Molly.
Thank you so much, Stella. That was an awesome presentation. And I even though I'm a women scientist myself, I still feel like I don't know enough about other women scientists who came before me. So I'm always happy to learn more about that. And yeah, it's been really fun being a part of the AAVSO ambassador program. And I think that they do a lot of good work at AAVSO, and I've been able to contribute lots of cool data as well. But yeah, and actually I got into AAVSO because of Stella. She dragged me in, so.
I'm very good at volunteering people.
All right, well, thank you again, and feel free to hang out. Our next guest tonight is Chris Elliott. He was going to show some.
Could I interrupt for a second? I do have a question,
yeah.
a comment actually. I really, really enjoyed Stella's presentation just now, but I wanted to point out that Stella's own organization, the AAVSO, has an incredible history of encouraging women to get into astronomy. when I joined back in the 1960s, Margaret Mayall was the longtime director of AAVSO, but I grew up and matured, I hope, a little bit there under the directorship of Janet Matty, who was here in Tucson a number of times and whom I was able to interview during one of the visits when she was here. And I finally got to meet Stella during one of her recent visits to Tucson, and really, really enjoyed your presentation tonight. Thank you. Thank you,
for
Stella.
having me. I hope to come back.
Thank you.
Yes.
I'd love to come back.
Hope you do. Hope you do.
Nice.
Yeah, absolutely. All right, so Chris Elliott was going to show us some live telescope views. Unfortunately, where he's at, it is clouded over. But he's been doing astrophotography out of Niagara Falls for about the last, Niagara Falls, New York, for about the last 9 years, and has a YouTube stream where he live streams a lot of astrophotography as well. So go ahead.
Yeah, so I wish it was yesterday. If only it was yesterday, because I was out here for about 5 hours as we got colored images as I use a monochrome camera out here. Right now, I'm in the midst of just transferring files from one to the other. So, because I use a dual PC or laptop to go through everything. So I have them saved on one. I'm just using the OneDrive and just going through. I can actually pull up. I don't know if I can. I'm not used to Zoom here. I'm used to YouTube, so I'm just trying to figure out how to share the screen here. Hang on. Oh, here we go.
I'd recommend sharing your whole screen. That works too.
Yep. So there we go. So there's one of the images. Now this is a stacked image that I took earlier this year in January. I don't know if everyone could see it of the Rosette Nebula, which is NGC 2244. This was taken just 8 images at 5 minutes apiece and stacked them using a hydrogen alpha filter, and then just used Deep Sky Stacker to stack them all together, and then used Photoshop to process the image. And I use this, I have my own shed, which I built. Took me about 6 months to build. And I have my own office, which is really, really cool. It is unbelievable. And I have other images here too that I can show you.
So what's your telescope rig?
So I have a CGEM 2 mount, and it is with a William Optics Zenith Star 80 millimeter refractor. It's an apochromatic with a USB filter wheel, and a Meade DSI 4. It's a sky imager, and it's a monochrome camera that I use, and have it all going through the house into the office.
Nice.
Yeah.
How's the light pollution in your area?
White. Terrible. It's probably the worst you can get. We have Niagara Falls to the north. We have Buffalo to the south. It is terrible. It is absolutely terrible. But with long exposures and hydrogen alpha, you can withstand anything.
Narrowband is the way.
It really is. I have 2 filters on the way. I'm going to be doing the Hubble palette, which is hydrogen alpha, oxygen 3, and sulfur 2.
Which brand did you end up going with?
I'm going to be going with ZWO.
Okay.
I mean, I looked at Astronomic. I looked at, there was a whole bunch of them. But I went with ZWO only because I have their light, the luminance, red, green, and blue. So I decided to just get the whole set of 7. So this way I have them all. And then the hydrogen alpha filter, that's a 7 nanometer.
Okay.
Let me see if I have, because I can pull up another one here. If I can just show color.
Sure.
It's remarkable that you can do the work that you do in those conditions. I'm always amazed at that.
Yeah. I mean,
I live just north of San Francisco in Oakland, and I do some wideband imaging, but I've been shifting more and more to narrowband. The results are just so much better.
Yeah.
Oh yeah, no doubt. Let me see if I can pull up a colored one here.
Sure. And it looks like you've got a microscope set up back there as well.
I do. So on my stream, what I do on YouTube is not only do I do on clear nights, I'll do telescope, but on cloudy nights, I'll do microscope. I'll look at blood cells. I'll look at, plant cells. I'll look at organisms, whether it's a rotifer or if it's a cilia, anything to just, last night I did, 2 nights ago, I did hot sauce and milk. I wanted to see what would happen with an acid and a base and see what happens with it. I did yeast, I did vinegar and baking soda, you name it, I do it.
That's really cool.
So here's a colored image I'm going to pull up here. Let me see if I can do this here.
Do you use one of your Astro cameras on
your
microscope?
Yeah, I do. I use what's called a T7. So it's an actually, you could probably see it. It's right here. And actually I have it looking right down into the microscope. And I mean, it's really cool. And I did what's called dark field. So what I did was, instead of actually going out and buying one, I used construction paper and actually cut a circle and put it right in front of the condenser. And what that does is it uses dark field, so you can actually see, it actually enlightens the edges around the actual organism. So you can see it's like a highlight instead of using the white field, which is, you can't really see much.
Yeah.
So here, I'm going to share this next one here.
Okay.
So this is the dumbbell.
Oh, yeah.
Yeah, this is M27, and this is using red, green, and blue filters. So with a monochrome camera, you have to do like 3-minute exposures. If you go to 5-minute exposures, take a whole set, flip it to green, do a whole bunch, flip it to blue, do a whole bunch, and then stack them. And then that's the colored image you get.
You got some great star colors in there.
Yeah. I mean, these I think were about 8-minute images. So these took a lot.
Yeah. Yeah. Yeah, so it's too bad it's cloudy where you're at, but thanks for showing us some of your images and talking about your setup.
Yeah.
I hope to have a shed at some point. I'm renting a house, so there's only so much I can do. But someday I'll have a cool big old backyard shed that I can have all 3 of my telescopes in.
The best way to do it is get a balcony. That's what I did for mine. I actually have a 2nd-story balcony that comes right out of the bedroom. And what I did was I bought an arrow shed. It's one of those metal sheds that you use that you buy at either Home Depot or whatever.
Right,
and then what I did was I rigged it. So all I did was I built it and built the roof on the side, and then used cabinetry. So in other words, you have the wheels, and how you pull out the cabinet, you have the wheels.
Right.
So I used those and then put the roof on it with the wheels, and then you could slide it back and forth. Insulated it from top to bottom using Artec board, put flooring on there, and then used an air conditioner heater, Wi-Fi, and put that in there. So I have the equipment in there so I can set the temperature in there year round, whether it's air conditioning or heating.
Smart.
That's awesome.
Yeah.
All right. Thanks for coming on, and hopefully next time it'll be clear.
I hope so. I really do.
You can tune into his YouTube channel for microscope and telescopic views on nights when it's actually clear.
Yep.
All right. Our next speaker is a good friend of mine, also from when I lived out in the Midwest, Terry Mann. Terry is the past president of the Astronomical League and is the current secretary. She's also the president of the Ohio chapter of the International Dark Sky Association, or IDA. She spends her time working on League projects, coordinating and co-hosting Astronomical League Live, and giving talks about imaging, light pollution, or astronomy. In her free time, you'll find Terry and her dog Tater, oh, that's cute, under the stars imaging or just enjoying the view. And Terry is going to talk tonight about the outreach efforts of the Astronomical League.
Well, thank you, Molly. I appreciate that. Let me share my screen here in a minute. There we go. All right. I've been on here before with the Astronomical League quite a bit. And what you might know or might not know, we've got about 18,000 members, a little over that, and about 304 societies divided into 10 regions across the US, and we have some international members. Now, what we've all noticed, I think it doesn't matter if you're a vendor, if you're an amateur astronomer, or where you're at, we have all seen an increased interest in astronomy. And with that increased interest, I thought it might be a good idea to tell all the new people, welcome to our world. You will have a talent of learning how not to sleep. Once the skies are clear, there's something about not wanting to go to bed because the stars are out. And sometimes, like in Ohio, we don't always have a lot of stars out. So that is definitely my talent, is not sleeping at night. So what I'd like to talk about a little bit is outreach, and about what this is, what it is, what it was, going to star parties and just hanging out with people, going out to dinner, being in talks, sitting shoulder to shoulder. And we can't do that right now. So it has really changed. Outreach now is exactly what you see right here. And we're all still doing it. We're all still active. We are just doing it in a different way. We've learned new skills and how to go about all of this. So I think what we're probably going to see once we get through all of this is we're going to probably go back to our star parties. And yet I think we're going to keep our skills that we've learned here, because we have learned how to reach out and do more things, to see more people, to take more classes, to go to different parts of the world and look at live views of the telescope. There is so many cool things we have learned that has really came out of this. So I think what we will see as we move forward is a combination. We're going to have a hybrid. I think it's going to not be a bit unusual to be at Alcon. This year it'll be virtual, but next year when we have Alcon, I bet you will still see a virtual component of that, because we can reach so many more people and have communications with so many more. Now, this is one of the things that you kind of have to deal with. I don't think you can talk about astronomy without talking about two other things. When you go out and you make plans, you're going to image or whatever, and all of a sudden you have clouds. Well, I went to an aurora conference up on the North Shore, Lake Superior, and I went to see the aurora. And instead, that's what I got. I had a blizzard. It was unbelievable. And that was from the deck of my hotel room. But that's one of the things we deal with. Another thing is light pollution. Just as Molly said, I'm president of the Ohio chapter. If we don't really start watching light pollution, we are going to lose our dark skies. And yes, we can use filters, but for people that are brand new to this, and for people that want to save a natural resource, we need to really start working on saving these dark skies. They're very important for wildlife, for health, for so many things. So you can't hardly talk, I can't talk outreach without talking about, always remember, it might not go as planned. You might have rain, you might have snow, and you might have clouds. So always remember that. But let me give you some resources and some ideas of what we kind of see, as far as outreach and things we can do. Now, the Astronomical League just started a YouTube page, and Molly was one of the women that has been interviewed by John Goss and David Levy. Both of them are fantastic talks. Please go to our website and check that out. One of the talk before the last that we did was from Norris Grice. And you can pick up, this is pretty much what it will look like.
And then almost at the same time, I would be getting.
And Norris is an amazing author. What she does is she has made Braille books for astronomy. Now, these are books that the images are embossed. It looks like on paper. They have the lines, the bumps, the textures. But as people come to the telescope, visually impaired people can feel what it is. And actually, if they could see even a little bit through the telescope, they can tell what they are looking at. And these books look incredible. I have ordered the two I could find. I don't have them yet, but I think these would be a great addition to any club, because it allows you to reach out to more people, maybe people that don't understand it in the way we do, or cannot see in the way we do. So it gives them some other way to communicate. And these books look amazing. One is called Touch the Stars, and the other is Everyone's Universe. And I think Touch the Universe is out of print, I believe. I can't find it anywhere. But seriously, look at these. It would be great for a club library. Another thing that I do, I am fortunate, I only live about an hour and 15 minutes from Serpent Mound. So when I'm giving talks around, this area, one of the things, Serpent Mound, there was a lot of talk about a meteor crater there at Serpent Mound. And that was one of the issues that I went into, and we discussed Serpent Mound. But when you bring astronomy home with your own landmark in that area, that really helps. And if Dave Eicher is still here, there's an amazing rock shop down by Serpent Mound. Just amazing things there. But this is another way to link astronomy, maybe in something that you have in your own property or in your own area that you can talk about. And one of the things that's hard to understand, especially for new people, and even, for me, is space and distance. I understand what it is, but trying to wrap my head around huge numbers. Okay, the diameter of the Milky Way is 100,000 light years, and that's what light travels in a year. Okay, I can't visualize 100,000 light years, but if you bring it down a little bit and talk about light traveling around Earth at 7 times a second, it brings it a little closer to me. Still mind-boggling, but to look at that, it brings it a little closer to help me understand a little bit. And I've found the more I can relate to something that someone can relate to, like if you have a picture of a galaxy and you have a picture of a moon, you ever notice the public is more drawn a lot of times to the moon because they can relate to that. They see that in the night sky. And this one, every year, this is my favorite thing to do, Perseid meteor shower. This is another one. When I do a talk and I have kids, I was fortunate enough to run into a meteorite dealer, and I told him I did outreach, and he gave me little chips of a meteor or a meteorite, and I took this to one of my talks. You tell some kids in an audience that when they see a meteor, especially the Perseid, it could be traveling about 130,000 miles an hour as it blazes across the sky, and you see their eyes get big. Well, then you tell them how big it actually started off. It could be a small pebble down to a grain of sand, and usually less than 1 to 2 grams. And then you hand them a tiny, tiny chip that they can hold in their hand and take home. It is amazing the kind of feedback from the scouts, from the girls that I have worked with. It is amazing what that does to a kid to put something in their hand from space that they can take home. It really hits home. And then one of the things when I was speaking at a senior citizens home, one of the senior citizens came out and they said, you know what I liked about your talk? You made me think. So many people come in here and they don't challenge us to think. And one of the things we spoke about was you can see 20 quadrillion miles at least. You give them a big number and they don't really realize what it is that can be seen out there. But Deneb and Cygnus is about 19 quadrillion miles. And then, many of us have seen the Andromeda Galaxy. Well, that's about 15 quintillion miles away. You start throwing things like that. Those are huge miles. They can't grasp that, but they might grasp being able to see this in the sky with their own eyes. And so that made a group of people really think that I was talking to, what you really can see. And I just ran across this. This is from Ohio State University Department of Physics. They have a monthly movie night, science fiction versus science fact. And I wish I would have seen the others tomorrow night. They're going to attack gravity and talk about what is fact and what is science fiction. And I want to watch this. But this is all the farther their schedule went was for tomorrow night. And I missed everything else. This looks amazing to me. It would be something so good to talk about, especially for sci-fi buffs, So that is another really high point that I think I would enjoy a lot. And I think others would too. And then we'll go back to the League. Now, if you go to League's website, and again, I apologize, we are rebuilding the website. It is going to take a while because we're going to overhaul the whole thing. It will take us a while, and so you might have some dead links. You know, you might not see exactly what you're wanting to see. And if that happens, please contact any of us that are on the contact page. All of these downloads are there for you to download, to copy, and to hand out at any event that you want to help kids understand. One of the greatest things that we have got is the first time you look through the telescope. We have got that, and all you have to do is just fill out the name and the date and the object. And oh my gosh, kids love it. And a few grandparents got a kick out of it too. So these are a real big hit. Definitely print them out and then fill them out as people are looking through it. It is really fun for both sides, I think. And then I'll talk a little bit about the League outreach program. We have this outreach program at 3 different levels. Our first level is if you do 5 events and each event must be 2 hours, you will earn a pin and a certificate. And this is a pin for a total of 10 hours of outreach. And all the paperwork that I'm talking about here is on the League website. Everything you need to download to fill in is there. We have a stellar outreach program, which you must have completed the award before, and you will add 50 more hours. So for the stellar outreach program, you'll do a total of 60 hours of outreach, and that is a certificate only. And then the master outreach. You have to have the other 2 awards before, a little bit more detail about what you need to fill out in the paperwork. For this is our highest, our master award in outreach for a total of 160 hours. And for this, you'll receive the certificate and the pin. I couldn't find a picture of the pin, but there is a pin that goes along with that.
For me, doing this tonight is the last couple of hours I need for the master level. So I'm really excited.
Exactly. And you know, for all the people, everything that we're doing online, it will make, it helps. It's still outreach. We've adapted to what we need to adapt to meet and reach other people. So I'm going to close with one of the things. We have Astronomical League Live coming up April 23rd. And as I said, our conference, the Astronomical League Conference, will be virtual this year. It will be August 19th through August 21st, and Scott will be broadcasting. So thank you, Molly. I sure appreciate it.
Thank you so much, Terry. And everybody who is involved in any kind of astronomy club or outreach or anything can take some of these ideas back to your club. You can work with the Astronomical League, or they have lots of resources, or just use some of these ideas to continue your club's outreach activities, which I know a lot of clubs have probably stopped doing during the pandemic. But it's really important to continue that. And now that everybody's kind of used to being online on Zoom calls and YouTube videos and stuff, I think we can still make a big impact.
Definitely.
All righty. Thank you so much, Terry. And our next speaker, double check. Okay, yeah. Our next speaker is a personal friend of mine, Sarah Krug. She majored in physics with a concentration in astrophysics and a minor in anthropology at the University of Notre Dame. While in college, she worked as an observatory assistant for an Astronomy 101 class and did research in star spots and gamma ray bursts. She has a PhD in electro-optics and photonics from the University of Dayton, where her dissertation focused on telescope design and image processing. Pre-COVID, she was a member of her local astronomy association, and she has volunteered for various outreach events over the last several years, including presentations at local star parties, helping with telescopes at a Girl Scout event, and giving optics demonstrations at grade schools. And Sarah's talk tonight is about archaeoastronomy. So Sarah, take it away.
Hi, thanks, Molly. Let me see if I can share my screen right now. Yeah, okay, good. It looks like it's gonna work. Can you see it or not? Share.
Yes.
Now it's working. All right, and let me make this full screen here. Actually, I'm gonna hold off on the full screen. So I want to start by saying that, yeah, as she said, my main focus is more in telescopes and astronomy, but I've always thought that archaeoastronomy is very, very cool. I came across it at one of my internships. Somebody else was doing research in this, and I've always wanted to know more about it. So I went ahead and took a look at it for tonight. And Terry Mann brought up Serpent Mound, and I actually, can you see the internet screen that I just pulled up, or do I need to do that?
You need to.
You'll need to share your whole screen if you're going to switch back and forth between.
Just checking.
So you just have to stop sharing and then start sharing again.
Yeah, let me pull that up then. All right.
Here, let me.
There we go. All right, so I'm going to new share, and then I'm going to pull up full screen. Share that.
Go.
There's Thor. Can you see Thor?
Yes, we see Thor.
All right, there we go. So now over on the right, you can actually see a picture of the end of Serpent Mound, and it turns out that Serpent Mound is the mouth of Serpent Mound is aligned with the sun setting on, or sun rising on the summer solstice. Cool. So this leads in actually very, very well into the idea of archaeoastronomy and what was used for, and kind of how it is used. So from there, I will go ahead and go into the slideshow. So to start, archaeoastronomy is defined as the study of beliefs and practices relating to the sky in the past, especially prehistoric times, and the uses to which people's knowledge of the sky was put. And I think a good starting point, a good question to ask is, why did prehistoric people look at the sky besides it being cool? And a simple response to that is that in farming societies, the seasons were very, very important. They needed to know when to plant food, when to harvest, when to get ready for winter. And being able to tell that from the solstices and the equinoxes was a matter of survival. It wasn't just a hobby. It wasn't just a job. They had to do it in order to live. And because of that, they've started looking at more and more things in the sky, such as the moon, and realizing that the phase of the moon and the cycles of the moon could be used to measure shorter periods within the solstices and the equinoxes. I believe I've heard somewhere that months and Monday actually come from the word moon. So yeah, since a month is about the same length as the phase cycle of the moon. And I believe that the importance of these cycles led ancient civilizations to start incorporating the sky and astronomy and what they saw into their religious beliefs and cultural events as well. So then they started looking at eclipses. They started looking at planets and comets and supernova and other things that showed up in the sky. And I'm going to show a few examples of different sites besides Serpent Mound around the world that are very, very interesting in terms of archaeoastronomy. So to start, I'm going to talk about Stonehenge. And Stonehenge, over the past century, there have been about 12 astronomical alignments that people have found and theorized that the Stonehenge can be used for. And some of the cycles and some of the alignments that they have found, it takes decades for a cycle to complete, which means that these ancient people were taking notes and observing the sky for possibly centuries before building and compiling centuries of knowledge before building this site. And the three most interesting points for me is, first, on sunrise for the summer solstice. If you can see my mouse here, the sun shines on the point of the heel stone over here on the top right, and it goes all the way through, and it hits the center of the altar at in the circle, and then it goes on back out from behind out behind the henge. A second thing that's really interesting is that the horseshoes in the middle, if you stand in one of those and you look out through a specific hole in the outer circle of stones, there are alignments with the moon rise and moon set for certain solstices when the moon is at its furthest points from the west and the east when it's rising. And a third thing, and I think this is the coolest, is if you see these outer circles of holes, one person has theorized that these outer circles or these outer holes could actually be used to place marker stones in. And if you place the marker stones in at certain intervals during the lunar or during lunar cycles, then they could be potentially be used to determine when the next lunar eclipse would be. So if it was used for that, that's really cool, and it almost turns it into a bit of a computer. So that is the first one. The second one, I kind of think is more interesting since I'm from the States and it's closer to home, is that Chaco Canyon in Colorado. And this was a site that was first settled in 200 AD, but the Anasazi turned it into a large city in 850 AD. And it actually contained buildings that were 4 to 5 stories tall and could hold up to 700 rooms. So this was a very large community. And a lot of these buildings look like they were aligned to different astronomical points, mostly solstices and such. For example, Casa Rinconada, which you can see over on the right, it's a big circle building, and it is believed that there were holes on the outside of this building that may have been used to predict the summer solstice. And there's another building a little bit further away from here that they believed might have done that with the winter solstice as well. The another interesting one was there's another large building. Whoops, there we go, called the Great House Pueblo, and it is aligned with a natural rock structure called Chimney Rock, which shows that when you look from the house to Chimney Rock, you will see the moon when it is at one of its lunar standstill points, which is basically, so the sun has 2 solstices in a year. The moon has 2 solstices, lunar solstices, in a month period. And however, since the moon is off by, or the moon's orbit is off by 5 degrees, its orbit actually precesses around the Earth in an 18.6 year cycle. So every 18.6 years, you are going to get a lunar solstice that is a little bit further away or from due east or due west, as you would usually get. And they have it aligned to that, which means that they were at least observing for at least 18 years to be able to get that point. All right, the most interesting part though of Chaco Canyon is actually on top of Fajada Butte, which is up or down on the bottom left. And there is a cliff face on the top of this. And on this cliff face, the Anasazi tribe had actually stacked a few large boulders such that when the sun was hitting them on the solar or on the winter and summer solstices, back behind the boulders on the cliff face, this dagger of light ended up intersecting one of these two large spiral petroglyphs. And this will only last 20 minutes, 2 days a year. So that's really cool. Unfortunately, they've actually closed this site down to the public because too many people were going up there and the stones were actually starting to get knocked over. But any images and pictures and videos that you can find of that is really interesting. The last site that I'm going to talk about today is actually Mayan culture as a whole. And it turns out that Mayan cities and temples are a gold mine for archaeoastronomy. There are multiple examples of buildings being aligned to the solstices. And there is even one case of one being aligned to Venus's cycle. And aside from that, there's other temples and buildings as well. For instance, this bottom left is a pyramid that has a carving of a Mayan serpent god on it. And this Mayan serpent god is the only thing on this side of the pyramid that is illuminated on the equinoxes, or at certain times of the day on the equinoxes. And it makes it look like the snake is coming down the stairs and coming onto Earth and getting ready to eat people. So that one's pretty cool. The second image that I've got here is El Caracol, which is believed to have been a Mayan observatory. And I think it actually looks like an observatory, modern observatory, which is really cool. And they have found 20 different sight lines for eclipses, equinoxes, solstices, and many other astronomical events. And that's only in the part that hasn't been knocked down. So there were probably more as well. On top of this, there are a few surviving Mayan books that have many, many astronomical charts of different events and cycles. And that includes the sun, moon, and planets. And it includes a 33-year chart predicting every single solar and lunar eclipse that could happen in the world. And it includes a correction scheme so that you can move that 33 years out anytime in the future. So being able to do that without any sort of computers is really amazing. So those are the three that I wanted to talk about today that I think are really interesting. There are plenty more out there. There's also a connected study called ethnoastronomy, which is the study of astronomy in different cultures, often in modern day. But I find it seems like the two really coincide a lot. So for instance, on the left here, this is a star chart that was on the ceiling of an Egyptian tomb. The center image is an very old Chinese set of constellations. And then on the right on the bottom right is a Hawaiian star compass that they used to teach sailors how to not get lost on the Pacific by using the stars and using astronomy. And all of these things are, it's amazing how people use this in the past when they actually needed it to survive instead of doing it as a hobby. And the way that they looked at it was different, and the things that they found were often spectacular. So I just wanted to raise some awareness of this interesting, sub study or field of sub-study. And if you can find some areas near you, it might make for some very interesting astrophotography. So I'll end with that. And if there's any questions or comments, go right ahead. That
was super cool, Sarah. Thank you.
Share. Did I unshare it? Can you?
I can unshare you.
Okay.
That's a great plan.
There you go.
Sorry about that. All right.
No problem.
Yeah, I think that stuff is super cool. And when I got to go to Peru in college, we learned a lot about the Inca connection to astronomy and lots of stuff that they built and plotted and stuff. And I'm always fascinated by what these ancient cultures were able to figure out by their observations and math and stuff like that. You know, when I'm sitting here with my calculator and internet access, you know.
Exactly.
Yeah, I'm hopping over to Facebook to see if there were any questions. Does anybody in the room have any questions?
Lots of great comments about the presentation. I think that archaeoastronomy is a favorite subject amongst many people. You know, it just lets us understand that humanity's, very survival was based on being able to understand the stars. And you know, it still continues today. So there's just this common thread that you can just, you know, look back just a little bit further, a little bit further, a little bit further, and you'll find that humanity is totally intertwined with astronomy. So.
And when you go out to a dark sky site and you get to see the Milky Way and just the many more stars than you can see in the city, you have to think that how could people not become obsessed with it? And I think every culture, even if it wasn't recorded, must have been obsessed with the motions of the fixed stars versus the unfixed stars, you know, the planets and stuff like that. And yeah, because you're just seeing this incredible sky every night. I think it would be hard to not become obsessed with it.
Yeah, it feels sacred, you know.
Yeah.
Good word for it. So.
I think the other thing is just the rediscovery by different cultures. You know, we're all in a self-discovery in our own way, and it's really neat to see that recorded from different cultures, and you know, the journey that they took to discover and interpret the universe and what they saw.
Yes. Agreed.
Yeah. Thank you so much, Sarah.
Thanks for having me today.
Yeah. Feel free to hang out if you so desire. But
and I love your necklace.
Yeah. Thank you. This one likes to flip over a lot, but this is my solar system necklace here. Yeah, we'll have to get together and chat some more soon. It's been a while. All right. Well, our next speaker, one more before we take a 10-minute break, is John Briggs. And I have TBD as a topic for you. So please go ahead and tell us about yourself and what you're going to talk about.
Okay. I'm especially interested in history of astronomy and history of instrumentation. And last week I joined the group, and Scott remembered the fun we had together at Mount Wilson a while back, where I had an unusual solar spectroscope that was made in the 1870s. And I thought it would be interesting to say more about it and share some pictures of it. And since Scott had brought it up last week, and because my internet link here in New Mexico is sometimes flaky, I sent the presentation ahead to Scott, and I think maybe he can share it for us from his screen. But I'll stay on live in case there are any questions or comments at the end of the presentation.
Okay,
that sounds super cool.
All right, so here we go. Let me put this in presentation mode, and there we are. So,
hi, this is John Briggs in New Mexico, and I'm going to speak today about astronomy of yesteryear, John Browning's solar spectroscope. I'm speaking from the Astronomical Lyceum in Magdalena, New Mexico, an informal museum of astronomy history. The volume is pretty low, Scott. Maybe you can crank it up. Although astronomers learned a lot about solar prominence.
Here, let me try something here.
I think there's an audio sharing feature in Zoom, if I recall.
Yeah, but there's something else I can do here.
Okay. Yeah, or something you can do through your streaming software, probably.
All right.
This is, of course, a total solar eclipses.
Better?
clever ones in the 19th century figured out you did not have.
All right, did not. Okay.
These are typical.
Let's see. Everything's turned up to 100%. But let me try one more thing here.
I think it's just not getting piped directly through to the stream. It sounds like it's coming over your microphone or something.
Yeah, hold on for just a second.
The 1870s,
better?
And astronomers were learning a lot about solar prominences. Look, it's labeled quiescent prominences. Here, all other sorts are being drawn and recorded, all of these without waiting for a total solar eclipse. How did they do it? They didn't have hydrogen alpha filters like we can take for granted now, filters that limit light so exactly just to the red of hydrogen gas. Nevertheless, they figured out how to do it with spectroscopy, as I'm going to demonstrate, and they made these kinds of drawings. Check out this drawing recorded by William Huggins in England, the first observation of a prominence in full sunshine. It's, well, primitive, a little crude, but it's impressive that he was able to see this without waiting for a total solar eclipse. As astronomers got better at the technique, especially through the 1870s, they got drawings more like this. Very impressive. This was recorded by a fellow named Trouvelot, a Frenchman who was an observer at Harvard College Observatory in the 1870s, and his astronomical artwork has become very famous. Now, most people interested in telescopes and astronomy have learned a little bit about how spectroscopes work along the way. In this case, this is a drawing of a simple spectroscope. They really are pretty simple to understand if you know about how telescopes work. In this case, there are really two telescope-like objects, the collimator, and the other one labeled as a telescope. But in between them is that triangle that represents a block of glass shaped, well, as a prism. So in this diagram, light is entering the collimator from the right-hand side, and there's an entrance aperture. S stands for slit. The light expands through the slit, fills the lens A collimates the light, which in other words turns the slit light into parallel rays. The parallel rays go through the prism P, but the prism spreads the light out into different colors. The lens B, further along the left, refocuses the light coming from the prism, and in the eyepiece of the telescope at the lower left, you actually see the rainbow-like spectrum of the light that was originally all mixed together coming in the slit on the right-hand side. That's basics of spectroscopes. And in fact, here's a real-life 19th century spectroscope, and you see the slit mechanism down there at the lower right. If this were attached to the telescope, the slit is where you would have the light from the main telescope lens or mirror focus an image of the sky or the sun or whatever light you wanted to analyze spectroscopically. In other words, turn it into its spread out colors and then measure the various brightness of the different colors. You can learn a lot about the physics of the light source from doing that type of thing. That's what physicists were figuring out in the middle of the 19th century. Now, astronomers were interested in celestial objects, so this here is a drawing of a widely opened slit. That's the black rectangle right in the middle. But notice the disk of light on the left-hand side with a couple spots on it. That disk of light is supposed to be an image of the sun with sunspots that's being focused right on the slit. However, just the edge of the sun is entering the widely open slit. So the relatively faint light that's coming there from the chromosphere and the prominences, that's the light that's actually entering the slit and going on through the spectroscope without being completely overwhelmed by the very bright light of the solar photosphere. If you set this upright, this is the result at the eyepiece of the spectroscope. Now, I think this is a little idealized. There's been some artistic liberty here, making it look easy how much of the chromospheric structure, in other words, the prominences, are visible in the hydrogen alpha absorption line of a solar spectroscope. But it illustrates the idea, and I can show you more realistically the way I've been able to record it myself. This is a picture that I took myself of the solar spectrum, but the spectrograph was tuned to the very wide and dark absorption line of hydrogen light, hydrogen alpha light, the red light of the sun. But that's what's in the center, the dark line, dark vertical line, which is really an image of the slit without that much light coming into it, because hydrogen isn't shining very brightly at that color. But notice there are some white spots. That's because I'd set up the spectroscope so that only the edge of the sun, the atmosphere of the sun, was entering this instrument, and at that spot on the edge of the solar disk, there was actually a prominence. So I am in this way imaging some prominence structure right through the spectroscope. Now, you're not seeing a lot of clear structure, but nevertheless, it made it possible to detect prominences, and with very careful adjustment of the instrument and manipulation of it and then drawing, astronomers of yesteryear could get pretty darn clear impressions of prominences by observing them through a spectroscope when it's tuned to the hydrogen alpha absorption line. It's really a pretty cool technique, but it's very old-fashioned nowadays. How did I do it? Well, it was way back in 1990, and I was lucky enough to have access to the famous Snow Horizontal Telescope at Mount Wilson that was designed to do things like this in solar spectroscopy. The two optical flat mirrors at the Snow Telescope capture sunlight and direct it down a long path into the darkened building, a path that's approximately horizontal. The sunbeam hits a 24-inch diameter paraboloid down there at the lower right in this picture, but then it reflects off the paraboloid, now finally being focused, and in this time exposure shot where the sunbeams are illuminated by dust in the air, the F30 paraboloid is focusing off an optical flat on the ceiling and forming an image on top of the white mechanism, the white table at the lower left of the picture. Built into that white mechanism and extending below it was a very large solar spectrograph. And here were students back in 1990 learning how to record these kinds of features. But 120 years before we were doing that at Mount Wilson, this is the kind of compact instrument that astronomers were using for similar pioneering observations of the sun. This here shows that same small spectroscope attached to the eyepiece end of a 6-inch refractor that was at Harvard College Observatory.
That's cool.
In England, the similar instruments looked like this. This example made by John Browning in London, an illustration out of his catalog from a design that was circa 1870 or maybe a little bit later. Here's the same thing in real life, beautifully tucked away in its storage case. Here it is assembled, or at least set up for laboratory use, because you could use it that way as well as attaching it to a telescope. This is the area that would screw into an English telescope a focuser using the standard threads they had in those days called RAS threads for Royal Astronomical Society. And inside there's a little bit of complication, but basically that was the entrance slit of this compact spectroscope. After passing through the slit, the light would continue through the tube, entering this picture on the right-hand side, but then finally pass through a lens on the end of the tube, and then the collimated light would enter this elaborate little prism train. The first block of glass the light entered looks like the prism that you might have taken out of a star diagonal that you'd be familiar with for modern times. The tube associated with the slit is on the left-hand side in this view, and you can see the light coming out of it goes right into the face of a prism there. And however, that prism directs the light onward through the entire chain of prisms that is linked together mechanically so as to stay in proper adjustment. The light is dispersed more and more as it passes from prism to prism. Finally, at what appears to be nearly the end of the train, over on the right-hand side, there's another block of glass that directs the well-dispersed light back through the same prisms, but on the bottom half of the prisms. Notice how the two brass tubes are actually at different levels. The one on the left is a little bit higher than the one on the right. That's because the light enters the lower right-hand tube coming out of the bottom of all those prisms. And that is how this thing works as actually a double pass spectroscope for effectively the total dispersing power of 10 prisms.
Wow.
That spreads the light out a lot in the solar spectrum, so you can see fine details in the rainbow-like spectrum. In this shot overview again, notice how all the prisms are clustered fairly tightly together relative to the metal disc underneath them. This is the same angle in the instrument, but if you notice compared to before, the prisms are now more spread out relative to the metal plate underneath them. That's because they're all linked together mechanically in such a way to maintain proper alignment as you make this adjustment, allowing you to sweep through the entire breadth of colors in the spectrum of the sun that you see in the eyepiece. So they're linked together kind of like the links in a scorpion's tail. Using small instruments like this, small but very elegant instruments, astronomers in the 19th century began to understand how spectacularly dynamic the solar spectrum could be. Here, a bright emission light is erupting in what is normally an absorption line in the solar spectrum. Some of the light is being blue shifted to one side, and other light from another part of the solar surface is being red shifted in the other direction. That's what's accounting for the odd squiggle of radiation that's in the middle of this field of view. It's caused by the very violent motion of the bright energized gas that the telescope was directed towards as it fed the light into the spectroscope. It's pretty neat stuff. one American telescope that was equipped with this kind of accessory right from its beginning is the 8-inch Elvin Clark refractor at Seagrave Memorial Observatory in North Scituate, Rhode Island. And this wonderful telescope and its instrumentation is maintained by the Skyscrapers Incorporated, the Astronomy Club of Rhode Island, and I'm proud to say that I'm still a member back there. If you want to learn more about the history of solar spectroscopy, there's a wonderful book that's on the internet free. It's a free download. It's from the 1880s and later editions, 1890s, simply entitled The Sun by Charles A. Young. Google it, download it, and you can learn all about this stuff. Many of my illustrations were taken from that book for this brief presentation. The Sun by Charles A. Young, a great book. Thanks for your attention.
Excellent.
That was cool. I'm fascinated with like old scientific instruments. Having grown up in a very digitized age, seeing how analog instruments work just kind of blows my mind a little bit.
It's very impressive looking at how detailed the delineation was back in the 1870s of solar prominences, thanks to this kind of visual spectroscopy. And we take fabulous hydrogen alpha filters for granted today, but in the old days, they had to work really hard to see the sun in hydrogen alpha, but they succeeded. And it's a beautiful instrument, and I'm grateful for your attention, sharing more about it. But my presentation was longer than I told Scott it would be, so he's tolerated that very politely. But I'll stifle myself, so maybe we can take the break now that we all deserve, I think.
We're running a little bit behind schedule at this point. But
one thing I would like to say, if you don't mind, Molly.
Yeah, go ahead.
Is that when we listen to a talk like John just gave, we're going back in time. And it's not as if, I feel the years, the days and the years and the nights are sliding away back to a different time and a different place. And I think this is directed maybe more at Libby than at all the others, who is so young and who represents in many ways the future of amateur astronomy and the night sky, because we are seeing what it was like to be alive at a different time. And it's so interesting to hear a speaker like John, who really can move us back so effectively into that time, show us the spectrograph, show us the telescope that took the spectrogram, and gave us a real sense of what it was like back then, before the age of computers. Libby will never know life without a computer. I don't know what she would do if she woke up one day and there were no computers allowed ever again. I don't know how she'd do it, and how her generation would do it. And I look forward to hearing some thoughts, both from her and from John, about what life would be like without the instruments that Libby has access to right now. John, good talk. Really enjoyed it. Thank you.
Thank you, David.
Yeah, that was really cool. Thank you.
Okay. Well, at this point, I guess we'll all take a 10-minute break. It's time to get a sandwich or something to drink, and we'll be right back with some more great talks here on the 39th Global Star Party with guest host Molly Wakeling.
These talks have been so good. Okay, time to go make a sandwich.
Time to go make a sandwich. That's right.
Yeah.
Dinner time.
It's a kind of a late dinner for those of you out on the East Coast right now.
Well, I worked till 8:30, and then I got here like immediately, so I haven't had time to eat.
Oh, really?
Yeah.
Yeah. Kind
I'll
of
be right
reminds
back.
me of the one that we did, the 24-hour one that we did at the conjunction of Jupiter and Saturn. It just went on and on and on for so long.
Oof.
And you might have said that was too much of a good thing, but it wasn't. I really loved it. I enjoyed it so much being on that.
I'll be right back. I'm just going to get something to eat real quick.
Yeah. Okay.
peanut butter and jelly sandwich required.
Well, David, this has been a great global star party.
I think so. I've really been enjoying it.
Yeah, me too. Yep.
I think it's been really very successful and unique. I'm really glad that we're doing this.
Yeah, me too. Yep. And yours is coming up next week, so.
Next week, yeah.
Mm-hmm.
Kind of an interesting line of speakers, but I'm thinking we may have slightly fewer than we have usually. But I don't know.
We'll
I'm
see.
open to suggestions.
Yeah.
But tonight is Molly's night, and we're very proud of her.
Absolutely. Absolutely. And we're all back now. Hope you enjoyed your short break and are ready for the next run here. We've got more exciting speakers to come. So Molly, take it away.
All right, welcome back. Hope everybody had a nice break. I managed to grab myself a PB&J and some chips and some cake that I made and put in the freezer and warmed back up, and now I have cake.
PB&J, chips, and cake.
Yeah. Oh, and apple juice in this really cool nebula cup that I have a set of 4 of with different nebulae on them.
Beautiful.
And plum wine for Passover.
Oh yeah. Yeah, okay, so now that we're back from break, we get to move on to the door prize segment of the show. And that would be with our own Terry Mann.
Ooh, thank you, Molly. I'm going to share my screen again. We're going to start with our starting slide that we always start with. A solar warning whenever you're using an optical instrument, not to look at the sun without protection for your eyes. Sunglasses aren't okay. You need an actual filter for whatever optical equipment you're using. And I wanted to announce we are going to start doing door prizes different starting in April. We will continue to ask and answer questions, but we are not going to announce the winners each week. We are going to be awarding prizes at the end of the month, and then we're going to add 2 grand prizes a year. So with every talk starting in April, a slide will be added at the end of the PowerPoint with the individual names that have given correct answers. And those names will go on an Excel sheet. And then at the end of the month and twice a year, we're going to use a number generator, choose the winners randomly from the list of names. And then, as I said, twice a year, we're going to do a grand prize, and all of the names will be added in at that time. So what we're looking at right now is we're thinking one of the grand prizes will be during Alcon in August, and the other one might be in December. So what you're going to see tonight is you're going to see me again, even after this one. I am going to give the answers from the 2 last star parties with their questions. Then tonight, I am going to ask my questions, and probably about a half hour later, I'm going to come back on and just give the answers for those 3 questions. So we can kind of wrap up the old style of door prizes so we can start new next month.
Cool.
So let's start with Global Star Party 37, which was March 16th. The question was, where do we find the star Betelgeuse? And that was in the constellation Orion. And the winner was Lauren Lemon.
Oh, congratulations.
Question 2, what is the name of the path of the sun, moon, and planets take across the sky as seen from Earth? That is the ecliptic. The winner is Jules Stewart. Question 3, what are the names of the 2 stars in the bowl of the Big Dipper that point to Polaris? And it's Dubé and Merrick. And the winner is Richard Grace. And those are the winners from the March 16th Global Star Party. Here are the winners from the March 23rd Global Star Party. How many planets in our solar system have no moons? It is 2, Mercury and Venus. And that is John Persichilli, won that one. The next one, what is the name of this northern constellation that seems to wind around the bowl of the Little Dipper? The answer is Draco the Dragon. Ernie Jacobs is the winner on that one. The third question, these 2 prominent features are visible from southern latitudes on Earth. What are they called? The Magellanic Clouds, and the winner is Suzanne Leap. Now, I'm going to ask the 3 questions for this star party, and we ask now that you send the answers to secretary@astroleague.org. So as I said, I'm going to send them in as fast as you can, probably within the next half hour or so. Yeah, I'm gonna be
busy. A real race, right?
Yes.
Okay. I like the tension. This is good.
Yeah, I'm going to be working with the door prizes behind the scenes here. Okay. And so in the next half hour, I'll be back to give the answers and the winner to these questions. And as I said, secretary@astroleague.org. Okay, here's the first question. What is the hottest planet in our solar system? Question 2, how many Earths can fit inside of the sun? Question 3, if you could lump together all the thousands of known asteroids in our solar system, their total mass wouldn't even equal 10% of the mass of the moon, Earth's moon. Is that true or false? And send the answers to secretary@astroleague.org. And I will be back in a little bit. Thank you very much.
Oh my goodness. was that applause from your end, Terry, or did Scott play that?
That was Scott.
Oh my gosh. Yeah, you need to get one of those like soundboards that like the super duper streamers use to, or like the radio hosts, that make different noises. Maybe no fart noises.
I only have a few. I mean,
there you go.
Good one here.
Oh my gosh. That's amazing.
Don't encourage him, Molly.
Please. That's right. So,
all right.
No mind to that man behind the curtain.
All right. Well, thank you, Terry. And we will have her back on in half an hour to announce the winners. So stay tuned. And there's also a lot of great talks in between now and when Terry comes back on to announce the winners that you should also stay tuned for, including our youngest guest, who has been a regular on this show and is a perfect example of how practice makes perfect. her presentations get better and better, and her obsession with space goes stronger and stronger. That is Libby in the Stars. Take it away, Libby.
Okay, today I'm talking about gravity. I made a presentation, added some cat photos at the end, because why not? So here's the beginning of the presentation. I quickly added cat photos, knowing that we were all cat fans, so that's at the end of the presentation, not the topic, but
you're already a professional. Welcome to the community.
So gravity. So gravity is like something that's like very hard to touch on because it's very hard to explain what it is because I usually just explain it as it is a force because you can't see gravity. So you can't really explain a lot of what it is and what it looks like and, you know, that stuff. So I usually just explain it as gravity is a force. And only the planets that have an atmosphere is, they have the gravity that pulls down to the center of the planet. So I remember once when I was at space camp, we were talking about gravity and we were talking about if we were on Jupiter, that like the gravity is stronger there, which would be pulling us to the center. And therefore it would be hard to lift our legs and walk around. And again, we were talking about how we were on another planet that was a little bit smaller, on how we would be able to walk a lot easier because the smaller the planet, the weaker the gravity is because the gravity, like the bigger the planet, there's more of that stronger gravity because it's pulling you down to Earth. And that's how everything on Earth works is if I dropped a cup of water, then it would fall straight to the ground because that's being pulled to Earth's center of gravity. And now if you were underwater, like say you're scuba diving, the farther you get down to the center of Earth, the more tighter it gets because you're being pulled in and the force is getting stronger and stronger. And we've actually touched a lot about this onto my school science class. We just started talking about it and I started a huge conversation between a lot of my classmates on the different gravity in between planets. And we were talking about zero gravity when like you're in space. And when you're in space, that you're in zero gravity, obviously, everyone knows that when you're in space, you're in zero gravity. And when you're in zero gravity, there's nothing really pulling you around or pushing you down to its core. You're not at the center of gravity or anything. And really, there's like, you're not being pulled anywhere and you're weightless. So like if you see the astronauts out into space on the International Space Station, they are just floating around because they're in zero gravity. And they're not really being pulled into any center of gravity around any of the planets or any of the moons because they're far away from that. So they're in zero gravity. So they're weightless. And when you're weightless, you're just floating around. And I was thinking about this and I kept on dropping something on the ground today, thinking about this, like the second that I let go of that and it's dropping, oh Lord, just a second. My mom just hacked my ceiling fan.
You're walking through space.
Okay, sorry. My ceiling fan has Bluetooth and sometimes my mom's phone randomly connects to it. So it just started playing music and I was like, oh snap. So back to where I was. So I was thinking about like astronauts on other planets. back when I was at space camp, there was a simulator there called the 1/8 simulator chair. And they strapped us into this chair, and there were all these springs like all over the place. And so they taught us a little bit about what the simulator was doing. And the simulator, basically Earth's pressure, like the gravity that's pulling us down, not Earth, the moon has 1/8 of Earth's gravity. So they called it the 1/8 chair. And I read a lot about this because it was like so interesting, because I wasn't even on the moon and I was experiencing like different gravity. And I was thinking, because like if I was on Mercury, then I would be floating around like crazy, because the pressure point, like Mercury is a small planet, so all the gravity that's pulling me down isn't very strong. And the same with the moon and with Pluto. So you would be floating around more than sticking to the ground like you would on Jupiter. Like Jupiter, if you look at its number, the higher it is, the more gravity there is that's pulling you down. Astronauts wouldn't be able to walk, so they would have their feet stuck to the ground trying to waddle around, because you can't lift your feet up in that gravity, because everything, like on each and every planet, the more gravity there is, the more you weigh. And I also was thinking about, like, what if you travel to the highest point on Earth? Like, let's say Mount Everest. What if you went to the top of that? You would actually weigh less, because you're not being pulled into the gravity of Earth, and it's starting to get weaker as you go out. So you would weigh less on top of you would weigh less on top of Mount Everest, and you would weigh heavier if you were all the way at the bottom of the sea, and like in the center of gravity in the Earth's core. So the rules of gravity, there's a lot of rules. I mean, there's a lot, but here's what I just came up with and researched a little bit about. Stars that don't have atmospheres, because there's honestly at any second a flame can randomly come out of a star into space. So there's no atmospheres. And the atmospheres, they also help with the gravity that's pulling you down. And we were touching a lot of this on recently in school, and we probably stormed all about this and argued about like what would happen if we sent an astronaut to a different planet, and what would happen for probably about an hour. And we came on the conclusion that like, and we never heard of like pressure points before. So if you were to look at the little measurements set with like all the difficult like signs on them, if you don't really understand, I mean, for me as a 5th grader, I don't really understand a lot of those symbols, but I could touch base of it on my classmates, and we started a raging conversation about that. And we were talking about what would be the easiest planet to go to, and what planet in the universe like has the hardest gravity, like, and then we were thinking of the size of the planet, because the planet would have to be big if the gravity would have to be strong, because the core of it would have to be strong. And I wanted to end it off today with some cat photos of my cat Bowie, because I was doing this presentation, and I quickly realized a lot of people in here were cat people, so I had some pictures of my own cat Bowie, and she's my space cat. She comes out to observe with me, so she has a little stroller, and we take her outside with us, and she'll sit out in the stroller, and I always read all of the new space books I get to her. And I always tell my mom, I said, if I don't become an astronaut, my cat will, because my cat's so smart. I always I always love to tell her stories about space, and I'm sure she gets very bored of it. But
that cat is so cute. Oh my goodness.
Yeah, I call it cat astrophotography as well as doing astronomy. You gotta
catastrophe, catastrophe, catastronomy.
Yeah, we used to take a lot of pictures of my cat when she was super young. This was like in the week that I got her. I still do take a lot of pictures of her, but I decided to add the younger ones because she's become a little sassy with me now and doesn't want to pose for me.
Oh my gosh, my cat does the same thing. As soon as I pull my phone out, they stop doing whatever cute thing they were just doing.
It's like my cat will be like so cute and everything. I take my phone out and I'll be like, oh, add this to my website or whatever, or I'll add this to my Facebook page, and then they just completely get out of pose.
Right? They know.
I think there's something like majestic between space and cats because it's like the perfect combination of both things that I've ever like seen in the universe. Because I remember a long time ago, I did a school project on Felicia, the France cat who went to space.
Oh yeah. Yeah, I think it's a very common sentiment that people love cats and people love space. When you put the two of them together, it's just an irresistible combination.
When you have some time, I have a question for Libby.
Go ahead.
Yes.
Okay, thanks, Libby. I enjoy each of your talks more and more than the one you gave the week before, and this one tops them all. But I do have a question and a little bit of difficult homework assignment to give you, because I had an argument about the very first line of your talk a number of years ago with Roy Bishop, who is a member of the Royal Astronomical Society of Canada and the smartest person I've ever known. I was reading in one of the editions of the Observer's Handbook, and Roy had written there that gravity is not a force. And as soon as you said that in the first line of your talk, gravity is a force, I thought, here is Libby versus Roy. And I wonder if you and Roy want to get into this together.
Oh dear.
Because I did with Roy. I talked with him for hours about it. He said, gravity is geometry. It is not a force. And he explained it strictly geometrically. And it certainly is that way. Of course, Newton thought it was a force, but Einstein kind of said, no, it's geometry. And that's what Roy Bishop says. And I still disagree with him on that. I agree with you, Libby. But I'm going to give you a little bit of homework to do, and maybe to get in touch with him and ask him to explain to you, an 11-year-old with the brain of a Nobel Prize winner, why gravity is not a force and why it is just geometry, which I think is a very powerful question. The other thing I have to say is that with the slide that you showed at the end, will you introduce us to a catadioptric telescope?
Yes, that's it.
Libby came up with a really good one before we did the show, and she was going to name a constellation after a cat, Cassiopeia.
Oh no.
Yes, Cassiopeia.
There's a serious lack of cats in the constellations. I think we need to add one more constellation to the 88 known.
But that's Cat's Eye Nebula.
I was just about to say the Cat's Eye Nebula.
Well,
Cat's Eye Nebula, my favorite
Leo
nebula.
the Lion is a very large
planetary.
cat.
True.
There's another aspect of Libby's talk where she mentioned that if a planet did not have an atmosphere, it would not have gravity. Now, I've seen both of those statements that they do and they don't on the internet. And I'm just wondering, in a talk about gravity, how does the group weigh in?
It's actually a fascinating deduction because if you look at the solar system, we have the smaller, all of the planets that don't have atmosphere are the smallest ones, right? You got Mercury and you've got Pluto, and you've got, the moon, for example, which have a less mass and therefore they don't have no gravity, but they have lower gravity, which I think is what you ended up saying later in your talk anyway. But it's a really fascinating deduction to look at the solar system and say, oh, well, obviously the planets that don't have atmospheres are the ones that have less gravity. And it turns out that those two aren't exactly connected that in that way, but I thought that was a really fascinating deduction that you made there. It ends up having more to do with the magnetic field around the planet and whether its core is still spinning or not. But it does so happen that the smaller bodies of the solar system are the ones that don't have atmospheres, and of course they have less mass and therefore lower gravity.
Dust, for example, and molecules and molecular clouds, I would suppose they would have to be coalescing not just by external forces, but mutual attraction by gravity.
And actually on the International Space Station, see Don Pettit, yeah, he one of the astronauts up there, he took a bag of water and little rock particles and kind of shook it up, and they immediately started forming clumps with each other as they kind of attracted each other, which is partly their gravitational force, partly their electromagnetic force. But yeah, everything that has mass, which is everything except for certain massless particles like photons, have gravity.
It was really funny.
A lot less than, the Earth.
It was really funny. Once I remember going to a space museum. They were teaching a lot about gravity in the little planetariums and how like the universe is on like a plain sheet of like gravity like that, and we're all being held together and it's all three-dimensional and stuff. And I remember going back home that night and I had the worst nightmare that we were all just on a blank like sheet of gravity out in nowhere just sailing along until our star dies.
That's kind of exactly what's happening. But very, very long time scale, billions of years. You won't be around when the sun dies, don't worry.
Here's some comments from our audience here. Norm Hughes is saying, I think if a planet spins, it will have some form of gravity, but could have no atmosphere. Harold Locke, if gravity is not, it is strange to me because it is almost the duplicate of electromagnetism. I learned in physics class it's described as an attraction of mass.
Yeah, and actually, that was one of the things that I thought was so incredible when I was an undergraduate in physics, taking my first physics courses, was that the equation that describes gravity is the same as the equation that describes the electromagnetic force, just with different constants. And that it just was so beautiful. And we now, it's an accepted part of the standard model that in the early, at the very, very, moments after the Big Bang, all four fundamental forces were actually one force. And we can kind of look at the four fundamental forces we see today, gravity, electromagnetism, and the weak and strong nuclear forces, as being four different sides of the same
thing. It's just
same coin or dice, if you will. Yeah.
John Paris Chili says, oh boy, let the arguments begin. I agree with the Royal of Astronomical, or the Royal of Canada. Gravity is not a force, rather it is a property of space-time and may not even be a property of our universe. Okay. There's
been some really interesting hypotheses on why gravity is so much weaker than the other forces. It's 10 to the power of -39, so 0.0000000 all up to 39 times weaker than the force that holds protons and neutrons together inside of the atom. And it's a lot weaker than if you just than you would expect. And there's some really interesting thoughts on why that might be that are still very much kind of in, like pre-theory, even just in hypothesis.
This is
Well,
like
Libby,
also
you
my
sure got
research.
something going today.
Davey
I'm
says,
no Newton.
Book Davey says, seems to me that gravity is a result of mass in space, but the jury is still out and I haven't got the math. Let's see. Martin Eastburn, who is, I think he's a physicist, he says, light bending of photons bend by gravity or two stars, or a black hole, and the star draws them in.
So heavy masses like galaxy clusters or individual black holes can they end up bending light around them as the light goes through their gravitational well. They're dipping in space-time. I could do a whole show on just this one topic, but I think we should probably start moving on to our next group of speakers.
All right.
Thank you so much, Libby. That was a great talk, and anything that stimulates some scientific discussion is always awesome. And you know, this is the kind of stuff we chit chat about in the graduate lounge at school. You know, in the physics graduate lounge. So it's always fun to have these discussions. Well, next up is one of my friends from this women's astrophotographers group known as Stella. I was going to have the founder of that group on tonight. She unfortunately wasn't able to make it. But we have Andrea here as a member of Stella. And she's a longtime visual astronomer and has just been getting into astrophotography. She's from Canada, and she remembers trying to use film to image the night sky, which I've heard many tales from various people on the extreme difficulty of using film as an astrophotography medium. And she's going to talk about hyperstar imaging. So Andrea, take it away.
Hi, I don't know how I'm going to follow all of that. I'm not a PhD. I don't have any degrees in physics. I'm a lawyer, and I practice law, and I do this for fun.
Just fine.
Can you see my screen, Molly?
Yes, so we're seeing the PowerPoint screen. If you want to go ahead and start the presentation.
Yeah.
There we go.
Perfect.
Yep.
So I will say I do have one sort of memory of when I really began to invest in equipment in this field. When I had my very first legal job and I had my first paycheck, I went and I got a telescope.
Good.
And then I told my mother I was going to a dark place in Toronto where there was going to meet people I hardly knew, and it was going to be totally dark. And she was very concerned. But it turns out we went there to watch Comet Shoemaker-Levy hit Jupiter. So that was with my very first telescope.
Awesome.
I was quite lucky that when I began the pandemic, I had already purchased sort of my next telescope. This was the next one up. And it's a Celestron 11-inch Schmidt Cassegrain. And it was kind of a beast, and it's very big and very heavy. And I got it out during the pandemic, and I really tried to learn how to use it. And it's a beautiful visual telescope. And then I thought, well, how can I possibly start doing imaging? Because that's what I always wanted to do. The only thing I ever did in the past was I had taken some film photographs of a solar eclipse in Aruba once. But now everything was digital, and my daughter was helping me take some comet pictures with digital. So I thought I could handle this. So I started doing lucky imaging, which is using a video camera to take images through the back of the telescope. And it turns out that's really a great way of doing planetary work. And I love this picture here. This was actually using an iPhone right at the eyepiece. And if you listen carefully, you can hear crickets. Oh, can you hear crickets?
I heard one.
Wait. Yeah, so this is me in my backyard, and the crickets were going like crazy. And I did a picture of Saturn, and I was hooked. That was the end. I actually managed to stack images from my iPhone, but it didn't look very nice. So I did end up using a simple little video camera through the prime focus, and I was able to capture some pretty nice planet images. Jupiter is still a work in progress, but I was happy with Mars and Saturn. But then I started thinking about how was I going to take photos of deep space objects. And if you can see from this screen, one of my really big issues was that an 11-inch Schmidt-Cassegrain telescope is 2,800 millimeter focal length. That is incredibly long focal length, very, very narrow field of view. Most people who use that telescope for imaging use a 0.7 reducer that takes it down to 1,980 or so. If you want to compare it to, say, a telephoto lens, that's more like 400, and your basic lens you get with your DSLR is about 50 millimeters. So this was a big challenge. These are two very famous YouTubers, Dylan O'Donnell and Trevor Jones. Both of them have C11s. Both of them use reducers, and both of them have massively giant mounts. And I didn't have that kind of mount. So, and they were struggling. If they have trouble getting images out of this system, then I figured I was never going to be able to do this, at least not right away. So that's why I ended up looking at the Hyperstar lens. It seems like this magical thing that turns a very, very slow telescope. So the C11 is f10 natively, and it converts it into a f1.9 lens, which is crazy, very, very fast. You'll see there's a picture of the front of the Schmidt-Cassegrain tube, and you take obviously that central mirror, you remove that, and you put the Hyperstar on. This is what it looks like on my telescope at home. As you can see, the camera attaches to the Hyperstar lens at the front. And I'm using an astronomical camera, a ZWO camera. So it is circular, so it kind of matches with the circular nature of the Hyperstar lens. I have seen people use a DSLR as well, but not for the smaller Schmidt-Cassegrains. They usually do sort of 9¼ inch and bigger. So basically it's made in the United States with Arizona. It makes a much wider field of view. You have to, if you go to order one of the Hyperstars, you have to specify, is it a C11, a C14, because the lens will change depending on what telescope you have. I have an Edge HD optic scope. If you have a standard Schmidt-Cassegrain, you would use a different lens. And similarly, if you have different cameras, there's different adapters. So you would have to get, in my case, I ordered the ZWO cooled camera adapter because that's the camera I have. And basically, this is how the Hyperstar works. On your left, you can see how the light comes in a typical Schmidt-Cassegrain telescope. It bounces twice before it gets to the lens at the back of the scope. With the Hyperstar, I seal off the eyepiece. I close it up. In fact, I tape it up so no light can get in. And where the red circle is, that's where we put the Hyperstar. So the light doesn't travel so far, so that's how the focal length gets reduced. I'm not a physicist. That's just my layman's analysis. So what happens now is I have a telescope that actually has a focal length of 540 millimeters, which is kind of like a telephoto lens, which is nice. It's not so narrow. And the trick about a very narrow field of view is you have to have precise guiding, and your little picture will often, your target will flow out of your field if you're not careful. But really the best part of it is it's f1.9. Now, if you have any photography background, you know that the lower the f-stop, the faster the lens, the more light it collects. If you compare f10 to f1.9, it is, according to Arizona, 27 times faster. So that's a lot more light in a much shorter amount of time. So what does that mean? It means you can do a full image in maybe a few hours one evening. Some of the tips and tricks that I've learned about mainly from other people is that it collects light so quickly, your stars get really, really bloated and overexposed quickly. So instead of doing, some people do 5-minute exposures, most hyperstar users do 60-second exposures, 30-second exposures. Some of them don't even guide because they are such short exposures. I tend to guide, so I have to mount a guide scope on the top. There is a place where you can put filters, so I often use a narrowband filter like the L Enhance. I use one-shot color cameras, so I don't use mono, but I do know people who do use mono cameras, and there is a drawer that you can slide different filters in and out, and because it's so fast, you're not needing to spend as much time. There is a Facebook group that I belong to, and it's full of people. We all do Hyperstar. We all share information. It's a great place to start if you'd like to try doing this. I will speak briefly about filters. There is something called bandwidth shift with fast optics. So if you're using a very, very narrow bandwidth filter, such as a hydrogen filter, 3 nanometers or 6 even, you may not get a very good performance at f1.9. So there's a lot of chatter about that. I use the L Enhance filter. A lot of people have trouble with the L Extreme filter. It doesn't really work very well on Hyperstar. It has super fast optics, like I mentioned, and as a result, there is a significant vignette, which is the bright circle in the center of your image. So I had to learn about flat frames and how to do flat frames and how do you do flat frames when your camera's right at the front. So you need a dew shield because you'll have to put a light panel on top of your dew shield. Some people do sky flats, which is pointing it at the sky. Even with sky flats, even with a light panel, you'll see I have cloth on top of my Hyperstar. It's so fast that if I do a sky flat at like half a second, I'm getting stars. So I have to dim it down if I want to get a flat frame at around a second and a half. But you can go after very dim targets. I try to go after dim targets because we can get lots of nice results in a very short amount of time. You do have to watch your cables at the front. You can arrange them in a special way so that you can have diffraction spikes. And if you don't like spikes, you can do it another way. You'd have to ask the experts on our Facebook group. And these are some of my images, which is the fun part. From left to right, I have the Cave Nebula. Below it is NGC 1333. It's a reflection nebula. I have the Tadpole and, of course, the Cone Nebula. I've also started doing a lot of galaxies with the Hyperstar, and I'm just getting used to them. And obviously, this is a Leo triplet. I have M74 and M81 and M82.
Wonderful.
And then these are just some other, these ones were done without filters. And so that shows how many stars I got when I didn't really use a narrowband filter. So the Crab Nebula was a broadband filter. So was the Flaming Star. And so are all of my galaxies. And that's the Cat's Eye Galaxy, Molly. So there's a cat for you.
Yay.
Yay. Yeah, there
Also,
should be more cats.
that looks great.
I have no cats. I could get my dog here. My dog is really cute. And this was my very first Hyperstar image, was the bubble. And I think Molly gave me some tips on how to process it. And it's really I think it's a great solution for a beginner like me.
Wonderful.
Awesome. Yeah. I've seen some people getting into Hyperstar. I've seen more people now that RASAs are a thing, get a RASA instead, which is quite similar. But the advantage of Hyperstar is that you can still image with your Schmidt-Cassegrain at prime, and do planetary work. So it's a very, very versatile telescope, the Schmidt-Cassegrain. And I've been too nervous to try Hyperstar just because it seems very finicky. So it makes me feel good that other people are finding success, because I might try it at some point. I have a C11 with a very floppy mirror, and then I have a C8 with a much less floppy mirror.
I mean, if you're finicky, there's things to be finicky about Hyperstar. Some people don't like the stars in the corners. I'm not very finicky. I'm pretty happy with most of my images.
Oh yeah, those images
look
that
great,
you
yeah.
made, that mosaic, I can just imagine a whole wall, you know, of prints done like that as you're walking into your hallway or your living room or something like that. It would just be amazing. So beautiful work.
Thank you.
Yeah, awesome. Thank you so much for coming on.
I might like to try to get a Hyperstar. How would I go about getting one?
Well, you would follow the link I just put in chat. You would go to starzona.com, and I'll put it in there again. And
The other reason I haven't done it is because the Hyperstar units are a little pricey, but still like less than getting another telescope to do those wide fields of view. Plus, you have.
Well, I was going to say, one of the things that I already had the dew heaters. I had all the stuff, the dew shield. Like I looked at buying another refractor, but I already had this. So
yeah,
it made sense to just buy the Hyperstar.
Yeah,
and the reducers are almost impossible to find right now. I have one on order. It's supposed to come in September.
Whoa! Like I know that there's been a lot of delays with Astro gear, but September is pretty extreme.
a lot of Astro gear in the industry with all the companies. It's running towards summer, the fall at this point. So much telescope gear was bought in 2020 that it exceeded any other kind of event, you know, including amazing events like Comet Shoemaker Levy 9 event, Comet Halley, Comet Hale-Bopp, the Mars opposition, the big Mars opposition. There was more telescopes bought during the pandemic than at any other time.
Crazy. They're probably also all stuck in the Suez Canal.
That's what we'd like to say, but that's not really the reason.
Yeah, I know.
Somebody said that there was.
It doesn't help.
Saying my telescope is in here, you know, pointing to a container on the on that giant ship. So anyhow.
All right. Oh, thank you again, Andrea. And if you have a Schmidt-Cassegrain, Hyperstar is worth looking into. You can do some really cool stuff with that. All right. Our next speaker is a friend of mine. I think we originally met at the Texas Star Party or something around there, but we've kind of stayed in touch. It's Will Young. I think you live down in Texas, right?
I do. Yeah. I guess y'all can hear me, right?
Yeah, and he's in the vicinity of where SpaceX does their Starship tests out there in Boca Chica. So he goes out and covers those events on his live stream, and he's going to talk about the Starship tests. Let's see. Oh no. Okay. Yeah. Sorry, I'm pulling up my introduction spreadsheet. Will is an avid visual astronomer from Texas who has combined his passion for astronomy with his love of music creation on his platform, Deep Sky Dude. His goal is to help inspire and educate the next generation of amateur astronomers and space fans. So Will, take it away.
Hey, thank you so much for inviting me, Molly. This is awesome. I've been watching these Explore Scientific broadcasts for since Scott started them, and it's been absolutely amazing. And like Andrea, I don't know how I'm going to follow the awesomeness that has been this evening. I mean, David Levy is here. David is one of the reasons that I got started in astronomy. Of course, Shoemaker Levy 9. I was a little kid. I was like, what is something's hitting Jupiter? And so, you know, and here I am 37 years old and still doing amateur astronomy. I guess I'm displaying my screen. Is it up here for everybody?
Yeah, it's fine.
Okay, awesome. So yeah, this is a shot that I took this last year at the El Dorado Star Party 2020. Which did go forward under heavy COVID restrictions, no talks, all kinds of social distancing, of course, masks in buildings, and everything was great. There was a lot fewer of us there though than normally, and I know Scott is very familiar with El Dorado Star Party's been many times with Explore Scientific. In fact, my friend won the grand prize one time, which was an ED 102. and he had the magic ticket that day. And but I promptly stole that scope from my friend, and have since done some insanely awesome stuff. I caught during the lunar eclipse the thing that hit the moon. I caught it with that. I did the solar eclipse with that telescope. So Scott, thank you from the bottom of my heart for that awesome gift that you gave me, because I have torn the sky open with that thing. So you're awesome.
You will. That's great.
And this is a shot from that El Dorado Star Party that I hope we can all get to one day and hang out with each other again. That's me at my scope. It's a 22. That's my main scope, I guess. Most astronomers have 3 or 4 toys we like to play with out there, right? And this is my main one. This is the 22-inch Obsession Dobsonian. I figured, go for it, right? I'm still young. I can still move things that are heavier, so I might as well do it now. And I've got a little warm room over there. Those ice fishing tents that you guys may or may not have seen on Amazon, eBay, or whatever. Those things are great, y'all. They're bottomless, so there's no bottom. You just put a tarp down or something, plop that thing right up there. It sets up super fast. And it's a great little warm room. You can have your table in there. If you're an astro imager, the wires can come in and out. It's great. And you can see my buddy Bram got a really big one. He got this massive snow tent, which is incredible. But he can actually put his Dobsonian in there. So let's see if I can go forward here. There we go. If you want to find me on social media, it's at Deep Sky Dude on everything: Instagram, Twitter, YouTube, whatever. If you go to deepskydude.com, that's where you'll find all my links to all my stuff that I'm doing out there. And like Molly said, I'm here to talk about Starship because that's where I am right now. I'm in a hotel room. This isn't an awesome green screen like most of y'all have, and I just picked the hotel background. It's an actual hotel. I've been here since, I don't even remember. I left like Thursday at 10 p.m. I got here at 5 a.m. and went straight to the park to try to watch 11 be launched. Well, it was a scrub. And so all weekend, we know they're not going to launch because of things. And then so Monday came, scrub. And then today was the foggiest day I've ever seen in my life. And they launched today, which was crazy. I'll talk about that here in a second. But these are the starships right here. You can see these massive rockets they've got down in South Texas. This is a SpaceX operation down here, a little place called Boca Chica, which is a tiny little town. It's the furthest south town in Texas, basically. It's on par with Brownsville, but maybe a little bit further south, about 1.5 miles from the Rio Grande. And both of these rockets right here, these are called the starships. Both of these rockets are dead or gone. They are no more. They have ceased to be. They were detonated. One of them on the pad just landed in hardcore, which I'll show you in a second. The other one landed and blew up 8 minutes later, which was a sad story for me because I put my lens cap back on my camera and walked away, and then the rocket exploded. This is what I'm shooting it down here with. This is an astronomy rig that I've been using too, to do sort of like Andrea's, like the wide field stuff, because I can go from 200 to 600 millimeter, and then I can digitally crop it down twice that. So I guess up to 1200 millimeter or so. And this is the setup I'm using here at Isla Blanca Park, which is where I'm at for this particular launch. And you can see the cameras pointed across the way towards where these rockets are launched from. It's about 5 miles south of our location in Isla Blanca Park, which is South Padre Island, if you're familiar with Texas. This was the launch of SN9. You can see the rocket there. It uses 3 engines. They're brand new engines from SpaceX, which is pretty interesting stuff. Again, I'm not a rocket expert. That's just, kind of what I've been doing the last several months, is coming down here and, just going out and oh, it's scrubbed. I guess I'm going back to the hotel for the rest of the day to take a nap or whatever. Go out there the next day. It might be the same story. They might fly. You never know. It's a test program. But SN9 did what we're seeing here. And this is the sort of the shot that I got, one of the shots. And unfortunately, when it came down, the engines exploded. Only one engine turned on properly, and it couldn't do the job of correcting the rocket, and it exploded. And that Pelican is now very famous. So good for that little Pelican. But this was the aftermath here. And notice that SN10, I showed you one with 2 rockets on the pad, still there, unharmed, amazingly. By some miracle, the shrapnel from this exploding rocket did not hit the other rocket. So it's pretty impressive. But you can see this road right here, and I'll tell you guys really quick, that's a public road. When they open Highway 4, Boca Chica Road as it's known, you can go out there. And that's where I was. I'm right across the street on public lands.
Wow.
Viewing it's a rocket facility, and this is the closest you can get. If y'all are into rockets, even just a little bit, guys, this will blow your mind down here. And there's something magical about a rocket launch. I don't know if any of y'all have ever been to one, filmed one, seen one, whatever. It is a magical experience, and especially out here, because this is a whole new program that has never existed before. And they're trying to land these things vertically on that cement pad where you can see there's sort of metal parts from SN9 everywhere. And you can see it vaporize the plastic on their fence right there. All that vaporized plastic is from the massive fireball. These are methane and oxygen engines versus like the Apollo with like RP1 or, what do they call it? I forget the name of the fuel, RP1, kerosene. It's basically kerosene. So these are methane engines, a little bit different. And I think that might be a clue to the issue that they're having out there. This is a video. I won't show the whole thing because it's a little too long, and I know we need to get moving here through some other guests and stuff, but I will just show the beginning and then I'll show the end. So this is right as the rocket, of course, takes off, and nobody's aware. The sound hasn't hit us yet, and it won't for several seconds. I think it's about 22 seconds or so. Somebody do the math there on how long it is, because I haven't really timed it. It's just so incredible to see it. It's just awe-inspiring. But the rocket goes up to 10 kilometers, and then it turns flat and falls back to Earth vertically with the engines off. Oops. So I'm not seeing my mouse cursor here. This is kind of weird. Let me just do it like this. The rocket, so here's the rocket falling back to Earth. Let's see if it'll allow me to do that. Okay, well, there we go. Sorry, guys, there we go. So they've turned the engines off. We're in free fall, 250 miles an hour. It's a grain silo, this thing. It's 160 tons empty. And I think they put I heard like something like 30 tons worth of fuel on board before they fly. It just boggles the mind when you stand up there next to this thing. You're like, how does that even get off of the gravity of Earth? How does it even free itself of those bounds? Like Levy was discussing earlier. I don't know how it does it, but it's an awe-inspiring thing. And it is astronomy in a way, because we can tie it back to we're on the side of a planet, where these creatures living on the side of a planet, launching these rockets into space. That's kind of astronomy a little bit. So that's how I tie it in. It's very sneaky, but that's how I do it. That's how I justify all these random trips down here. So what they'll do is, after they free fall until or right at about a kilometer, they'll turn on. Now they turn on all three engines. They used to only turn on two. When one fails, you don't have enough to right yourself. So you'll see them turn on the three engines. The vehicle will right itself vertically and hopefully hit 0 miles an hour at 0 feet, where the launch pad is. This is SN10, Starship serial number 10. It got really close. In fact, you can see here, it is landing technically. This 160-ton behemoth landed at 22 miles an hour. So it was just enough to crack the egg, if you will. This thing is thinner than a Coke can at its scale. So 22 miles an hour cracked something, and there was a leak, a methane leak or something, and that's had a fire going, and then the tank boiled and exploded 8.5 minutes later. Well, again, I put my lens cap on. We all thought the launch was over. We were congratulating each other on a job well done for days and days of waiting for this thing to go off. And I watched it visibly with my eyes right across the island there explode, which I didn't get on camera, and I regret that. But that's the way things go. Don't stop filming ever, guys. That's the lesson I learned that day. So if you're in Texas, if you're around Texas and you want to do this, it is definitely something you should do, because even if they don't have a launch, you can go out to the site area and just observe these things up close and personal if you want. And while I was down here, to tie it all back into astronomy here as I close it out, this was taken the last time I was here, which was earlier this month, for a different launch. That was 10. And you can see this is a cell phone picture. I'm not winning any prizes with this one, but I was super stoked to see what I saw because I've never seen it before. So there's Centaurus, a constellation most of us are familiar with, but there's the top 3 stars in the Southern Cross: Ga Crux, B Crux, and Delta Crucis. I don't know. And there's the Isla Blanca Park where I shoot all these launches from. And I was just walking along the beach and I was like, wow, Centaurus is really high. And I was like, I wonder if the Southern Cross is up. And so because I've never seen it, and I looked and all 3 of the top stars were, and the bottom one came up later, but it would have been at like 3 a.m. and it would have been low in the high pressure sodium lights of Isla Blanca. So I was like, I'm just gonna say I saw the top 3 and we'll deal with that later when I go to the Southern Hemisphere. And so yeah, that was a whole cool thing. If you want to follow me on Instagram and all these places, these are the kind of videos I post now, which have been wildly popular on Instagram. I can't even believe the kind of results I'm getting on Instagram. It's pretty insane. But this is done with the night vision monocular. So imagine a telescope, night vision, like military grade night vision, rammed into where the eyepiece goes, and then an eyepiece on that too. And then I just take my cell phone. We're talking about cell phone astrophotography, which great job, Andrea. It's great stuff. And I ran video on the Crab Nebula, Messier 1, as a lot of us have probably seen this in a scope. I think Andrea even had a picture of it. So it was an awesome picture. But this is what it looks like with just a telescope and an image intensifier. These are military grade. But anybody can get them as long as you're willing to sign the paperwork for it and pay the fee, pay the tax to amplify the light. But I look at this as kind of a light microphone, right? The telescope takes in the light, this device takes it in, it turns it into electrical energy, amplifies that electrical energy, and then turns that electrical energy back into video or visible energy, right? And that's how we see the image through the night vision monocular. It's a brilliant technique. I don't pretend to understand it fully, but you can produce stuff like this. And I always, when I put a little video on Instagram, you see I put stuff in there about the object if I can. Like the archaeoastronomy ties right in because the supernova pictograph in Chaco Canyon is about this supernova back in 1054 AD. So that's what I've heard. And Chinese astronomers also noted it at the time. I think Arabic astronomers as well, right there in Taurus. And then now we get to view the beautiful Crab Nebula. But that's it for me. Again, I'm Will. I'm the Deep Sky Dude. You can follow me on all those platforms that are out there for some reason. There's so many platforms, but I appreciate so much the time tonight and to be in the crowd that I'm in. I mean, David Eicher being here, the Real Reality Show. I mean, I love that stuff. It's so cool. So Molly, thank you so much for inviting me. And I'm forever in your debt. So thank you.
Yeah, absolutely. Thank you so much for coming on. And I love, you do stuff that's a little bit different than all the other astrophotography that I'm in all the time on social media, the night vision stuff and the Starship tests are really cool. And I wish I lived somewhere closer sometimes to either Cape Canaveral or down there to be able to witness those. It's got to be something else to see.
It is, absolutely. Yeah.
That's really cool. All right, you can stop sharing your screen and feel free to hang out as much longer for the rest of the show as you feel like.
Awesome.
Yeah, thanks so much for coming on. That was really awesome. That was a lot of fun.